Ashok sir is joining, Simon?
Yes, sir. Who? Ashok sir will join shortly.
Okay, right.
Ali sir has joined. Good evening, Ali sir.
Hi,
Ali
good
sir.
evening, Ali sir.
Mukaddas sir.
Good evening, sir. Good evening.
I think almost everybody joined. I think Ashok there, sir, and then
Yes,
Simon.
yes, sir.
Joining,
Short,
join. I think we can start by 6:30. Is it not? Huh?
Yes, sir.
Oh my God. Mouse काम नहीं कर रहा है.
Hello.
Hey, hello, Professor Kish.
Oh, hi. Do you hear me?
Yeah, good evening. This is Ben from Hong Kong.
Oh, hi, Ben. How are you? Long time no see.
Yeah, long time no see. I miss you.
I miss you too.
I'm very pleased to see you here.
Me too. It's really, I like to see you. Unfortunately, we missed you and to see you in Montreal because of this problem that happened.
Right. Yeah,
Yeah.
it's a pity.
Is the meeting started?
I don't know. I'm waiting for the
No, sir. Not yet, sir. We are going to start.
Oh, okay.
Professor Taimur Khan. I'm Professor M. Ali Ahmed from NIT Silchar, sir. Meeting has not started yet. We are just waiting. Dr.
Okay.
Khan, are you online? Taimur? Sir, please discuss.
Okay.
Formal meeting has not started. You can talk. No
Okay.
issue.
Professor Ahmad
Dr.
Kishk, good evening and good morning from NIT Silchar. Myself, Dr. Taimur Khan.
Hi, how are you? Good to
Good,
meet
sir.
you.
Good. I'm good. What about you?
I'm fine.
Okay, sir. Thank you. Very shortly, we are going to start because our director is another meeting. He's saying that within 5 minutes he will join us.
Okay.
Okay. Good evening, Ashok Day, sir.
Good evening, everybody.
Hi,
Good evening, sir. Good evening.
morning, our time.
Sir, I apologize from everybody because of this 5-minute delay. Very shortly, we are going to formal inaugural session. We are waiting for our director. He is on another meeting. Good evening, Director sir.
Good evening.
I think now we should start the inaugural session because we are already 9 minutes late. Sir,
Okay.
Director sir, can I start that?
Yes, please.
Okay, thank you. Well, good evening, good afternoon, and good morning, everyone. The ongoing global pandemic situation due to COVID-19 has unfortunately interrupted exchange of information among the scientific community through the conventional in-person gathering in different workshops, conference among the scientific, etc. However, we believe that learning and knowledge exchange even in these times should not stop. In these uncertain times, virtual mode of communication have come up as a productive alternative and made it much easier for all of us to connect globally. In this presentation is not okay. Sorry. Doesn't know. Okay. Just. Give me a moment.
Hello.
I am sorry for this interruption because of some technical issue was there on my side. Is the screen visible to all?
Yes.
Yes.
Okay.
Yes, can it's visible.
Yeah.
Visible.
No. Good evening, good afternoon, and good morning to everyone. The ongoing global pandemic situation due to COVID-19 has unfortunately interrupted exchange of information among the scientific community throughout the conventional in-person gathering in different workshops, conferences, etc. However, we believe that learning and knowledge exchange even in this time should not stop. In these uncertain times, virtual mode of communication has come up as a productive alternative and made it much easier for all of us to connect globally. In this spirit, National Institute of Technology, Silchar, India, in association with Delhi Technological University, Delhi, India, and Queen's University, Kingston, Canada, has aspired to bring and connect the scientific community through this 1 week long virtual course. So, with this immense pleasure and gratitude, I, Dr. Taimur Khan, convener of this webinar course, on the behalf of organizing committee, welcome you all to this 1 week long Indo-Canada SPARC course on dielectric resonator and its applications, DRA-2020, hosted by Electronics and Communication Engineering Department, NIT Silchar. DRA-2020 is a week-long workshop on the fundamental aspects of dielectric resonators and its engineering applications. The aim of this week-long course is to provide a common platform to the researchers working in the emerging area of dielectric resonators and allied domains for delivering talk in their specialized research topics. The webinar course structure is designed in such a way that the students, research scholars, faculty members, and industry professionals will get an exposure to familiarize themselves towards the recent developments pertaining to the dielectric resonators. At the same time, it will include in-depth discussion on various design challenges that are encountered in these fields and their possible solutions. The webinar course will provide not only the essential knowledge, but also a platform to the participants for exchanging their ideas and information with the distinguished invited speakers. This webinar course is fully sponsored by Ministry of Education, formerly Ministry of Human Resource and Development, Government of India, under the Scheme for Promotion of Academic and Research Collaboration, SPARC, as an academic deliverable of the ongoing SPARC project here at NIT Silchar. SPARC aims at improving the research ecosystem of India's higher educational institution by facilitating academic and research collaboration between Indian institutions and the best institution in the world from 28 selected nations. The major outcome of the SPARC initiative is to make the strong research collaboration between Indian research groups with best-in-class faculty and renowned research groups in the leading universities of the world in areas that are at the cutting edge of science or with direct social relevance to the mankind, especially of India. Now, on the behalf of organizing committee, I would take this opportunity to welcome our respected director, Professor Shivaji Bandyopadhyay, Dean Research and Consultancy, Professor M. Ali Ahmed, Institute SPARC Coordinator, Professor Upendra Kumar, Chairperson of this webinar course, Professor K.L. Vaishnav, and all other invited guests who have graciously agreed to attend this virtual inaugural session. Now, my warm welcome to SPARC team, Professor Yahya M. Antar, Foreign PI from Queen's University, Canada, Professor Frondorfer, Foreign Co-PI from Queen's University, Canada, and Professor Ashok Dey, Indian Co-PI from Delhi Technological University, Delhi, who have kindly agreed to organize this webinar course. My sincere gratitude to all the distinguished speakers, Professor Yahya Antar from Queen's University, Canada, Professor Ahmed Akish from Concordia University, Canada, Professor Wok Young from City University of Hong Kong, Professor Tayyab A. Danidni from Université de Quebec, Canada, Dr. Surendra Pal, distinguished scientist from ISRO Satellite Center, Bengaluru, India, Professor R.K. Gangwa from Indian Institute of Technology, IIT ISM Dhanbad, India, Professor Bhaskar Gupta from Jadavpur University, Calcutta, India, and Dr. Soni Kiran Kumar Das from Southern University of Science and Technology, China, who have accepted our invitation for this webinar course and agreed to share their knowledge with the registered participant in their respective areas of expertise. I also welcome members of the organizing committee of this event, DRA 2020, Dr. Ripon Patgiri, Dr. Naresh Babu, Dr. Saroj Kumar Viswas, Dr. Partha Pakre, Dr. Ranjay Hajra, Mr. Manas Mahanta, and Mr. Najmul, and they appreciate them for their willingness and command in managing different activities associated to this virtual platform on which we all are connected this evening and will continue so far for the next 5 days. In last but not least, I extend my warmest welcome to all the participants belonging to different parts of the globe, irrespective of their different time zones, who have registered for this webinar course, and hope that the 5 days of webinar course will be beneficial to all of them. Now, in continuation to further proceeding, first of all, I would like to call upon the chairperson of DRA 2020, Professor K.L. Vaishnav, to share a few words about the event DRA 2020.
Very good morning, good evening, good afternoon to all. Our Honorable Director, Sir, Professor Shivaji Bandyopadhyay, other distinguished and esteemed speakers, Professor Ashok Dey from Delhi University, Queen University of Canada. I can see that Professor Surendra Pal, then Professor from Hong Kong University, Professor Ahmed from Concordia University of Canada. Then there are so many galaxy of really experts. One of our alumni also part of these experts, Professor R.K. Gangwar from IIT ISM Dhanbad. I am extremely thankful to the all the speakers really for coming forward and given consent to share their experiences, vast experience to the participants. And I'm extremely thankful to Professor Ashok De of Delhi University and Professor Y.M. Antar for long association with the United Futures. We have seen already they have published one book chapter on this directive materials. In, I think, Springers, they already published, and it's getting a wide popularities across the globes. This really bringing laurel to the institutes. This project, the motivation to bring together researchers from the abroads with the Indian researchers and to give a strong foundation to the newcomers. We have a students, we have a BTech students, we have a MTech students, we have a PhD scholars. In the departments, we see we have a more than 100 research scholars that working in the different domains of other than part-time PhD scholars. So we have a big potentials. We need to jump to the bigger job. Our directors are Professor Shivaji Bandyopadhyay, really very much cooperative, great visionary. And under his leadership, we all are really getting extra fuel to work for the better of the institutes. And we see that Taimur has already pointed out the 330 participants for the different part of the globes. That's really bringing better visibility of the departments as well as the institutes. We look forward more bigger collaborations. Today we started with the SPARCs. Today we'll think of new projects. Because department has 31 faculties, as already Taimur pointed out, that this is an interdisciplinary. So there are different PhD scholar faculty may be motivated to work on this. I hope that this workshop will unfold many opportunities for the faculties, for the students, for the participants. And I congratulate the organizers, Professor Ashok De, Professor Y.M. Antar, and our Dr. Taimur Khan, the great initiative bringing all together and to give a new shape, the dimension of, the direction of dialective materials. I congratulate Dr. Khan. I congratulate entire team. We have seen that as it is a virtual mode, we see that there are so many background operations are there. I thankful to Dr. Pakre, Dr. Ripons, Dr. Suresh Babu, Dr. Manoj, and then Nazrul. Entire team really worked hard and working hard. With this, I wish that all the participants will enjoy these 5-day sessions. I also request to all our students who were registers to capitalize these great opportunities for the better cause of the societies. With this, thank you. Thank you and over to Dr. Khan.
Thank you, Professor Vaishnav. Now I would now request Institute Coordinator SPARC, Professor Upendra Kumar, to speak a few words.
Good evening.
Good evening.
I am audible. Am I audible?
Yes, you are audible.
Very good evening to our Honorable Director, Sir, Professor Shivaji Bandyopadhyay, Dean, Research and Consultancy, Professor M.A. Ahmed, Head of the Department, Dr. K.L. Vaishnav, all the expert speakers, faculty members, and participants. It is my great pleasure and honor to welcome you all in this inauguration ceremony of the Indo-Canadian SPARC course DRA 2020. This course is a part of the SPARC project of Dr. T. Khan and Dr. Ashok De, which is in collaboration with the international PI Professor Yahya and Professor Ferndufer of Queen's University, Canada. SPARC is a MHRD Government of India project and aim at improving the research ecosystem of India's higher educational institute by facilitating academic and research collaboration between Indian institute and the best institutes in the world from 28 selected nations to jointly solve problems of national or and international relevance. Currently, we are having 4 such projects at NIT Silchar. We have also applied for the 14 numbers of new SPARC project for the year 2020-21, and we are hoping to get good numbers of projects. I would like to thank all of you for participating in this program. Special thanks to the expert speakers for giving their valuable time for the course. Thanks to SPARC MHRD. We are also grateful to our director, sir, for giving his constant support and encouragement. And I also like to thank our convener, Dr. T. Khan, for organizing this Indo-Canada SPARC course, DSRA 2020. Let us make this program, that is course, a great success. Thank you all. Have a nice day.
Thank
Over
you.
to Dr. Khan.
Okay, thank you. Thank you, Professor Kumar. Now, in the continuation, I would now request Dean Research and Consultancy, Professor M. Ali Ahmad, to share a few words for the gathering.
Yeah, thank you, Dr. Khan. Am I audible?
Yes, sir, you are audible.
Okay, thank you. Good afternoon, good evening, and good morning to all the experts, the participants over the globes. Respected Director NIT Silchar, Professor Shivaji Bandyopadhyay, Professor Ashok De, Professor Ahmed, Professor Ben Leung, and other national and international galaxy of experts, Professor U. Kumar, the coordinator of the SPARC project, NIT Silchar, Professor K.L. Vaishnav, PhD and Chairperson of the course, Professor Khan, the coordinator and other coordinators of the course, and all the participants of the course. I, on behalf of the Institute, I welcome all of you to NIT Silchar. Hopefully, as soon as the pandemic situation over, I would like to have all the experts in NIT Silchar. Thank you very much, sir, for joining us in virtual mode.
Thank you, sir. Thank you.
In NIT Silchar, we have about 55 number of high-value project, national and international project. Out of that, 4 number of SPARC project, including this Dr. Khan's another project. So I hope, Dr. Khan, this is your second program during this pandemic situation under this project, is not it?
Yes, 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 sir.
Okay. Congratulations, Dr. Khan,
Thank you.
for continuation in this line and successful completion of the in the line of completion of the project.
Thank you, sir. Thank you.
About NIT Silchar academic cultures, just to have a glimpse of this, we have 6 BTech program, 15 MTech program, 3 MSc program, 1 MBA program, and PhD in all the departments of the institute. We have currently about 800 PhD scholars. Out of that, about 550 scholars are regular and staying in the institute itself. during this pandemic situation, our PhD program or other project org was not hampered at all, though we were conducting everything online. Even the convocation has been conducted online. To promote the research culture among the among the undergraduate students, we have undergraduate research council. We conduct annual research conclave every year, where the BTech, MTech, and PhD, all the students used to participate. We encourage all the students to join various conferences and workshops over the national or international in nature. I will request all the participants of the workshop so that they take the full opportunity during this course and concentrate themselves so that they can finalize maybe their MTech research topic, maybe their PhD research topic. And I would like all of researchers globally so that they work on translational research, that is international in nature, and to solve the real problem of the society, to make the present world a better place to live in. With this, I will like to thank again everybody. Thank you, Dr. Khan, to invite me. Over to you, Dr. Khan.
Thank you. Thank you. Thank you very much, Professor Ahmad. Now it was supposed to be here, Professor Yahya Antar, but recently I received a message from him that he is busy in some other 2 consecutive meeting of IEEE. In that continuation, like now, I would like to invite Professor Ashok Dey, ex-director, NIT Patna, to share a few words on the behalf of SPARC team.
Thank you, Dr. Khan, and good afternoon to all the Indian participants, and good morning and good evening to all other participants from different parts of the globe. Firstly, I want to thank Professor Shivaji Bandyopadhyay, the director of NIT Silchar, for giving this second opportunity to organize this type of program to under this particular SPARC project. Previous program was very successful. I am sure that this program will also become very much successful and useful to all the participants. I want to thank all the faculty members, deans, and other members from NIT Silchar for their cooperation. And also, I want to thank all the distinguished speakers from different universities of the world for agreeing to give lecture in this particular program. And with their knowledge, all the participants will be enlightened, and it will be a very useful program for them. And with these few words, I again welcome all the participants in this particular program, and all other faculty members and students from NIT Silchar, and also all the distinguished speakers from all over the world in this particular webinar DRA 2020. With this, again, thank you very much.
Thank you, sir.
Thank Taimur for organizing this program under this SPARC project. Thank you very much.
Thank you, sir. Thank you very much. Now, with great honor, I would now request our distinguished director, Professor Shivaji Bandyopadhyay, to address the gathering.
Yeah, Good morning, Professor Ahmed Kishk. Good evening, Professor Ashok De, my colleagues from NIT Silchar and other places across the globe, and the dear participants, good number of 337. It is indeed a great pleasure that is during this period when everyone is going online. So Dr. Khan and Professor De and Professor Antar, so they are organizing programs as part of the SPARC project. And I understand that this was actually supposed to be not an workshop, but a course basically. And in terms of the number of credit hours, so this could have been an 1 credit course. So those participants, basically the students who have participated there. Because I am also the PI of another SPARC project where we organize the course as a 40-hour course, and a full 3 credit score was given to the participants also after an examination process. So there lies the advantage of the SPARC, that is to take the relationships with the foreign collaborator to the next level. Now, to all our participants who are either on the Google Meet or on the YouTube channel, just to share that is NIT Silchar. We have taken up research and innovation as our key focus. And as we say, that is through research, we are basically trying to improve our standing. And when you do research, it is not only in terms of the publications or patents, but also in terms of the contribution that we make to the society, either through industry or through other applications. Translational research, what we call them. Then interdisciplinary, collaborative, internationalization, as well as collaboration with industry. And I do believe that the path that we have taken up, that not only takes care of the undergraduate, PhD and the master students, but also the bachelor students, undergraduate students, who also they remain abreast with the state-of-the-art technologies. And I understand that in this particular program, 5-day-long program, so we have students across the various levels. So it will be a great thing. That is when the great minds are at the speakers, and at the listener level, there are excellent people also. So a lot of deliberations will take place, and from that, new directions, new research ideas will be coming out. And many of the participants will be taking up new research domain areas to continue further. I wish the course on dielectric resonator and its applications a grand success. Thank you.
Thank you, sir. Thank you very much. Now, finally, before concluding this inaugural session, because in continuation there is first lecture of this first day. For that, Professor Wok Wa Leong from Hong Kong University is with us. Before inviting him for the lecture, I would like to read his short biography. Professor Leong was born in Hong Kong. He received the BSc degree in electronics and the PhD degree in electronics engineering from Chinese University of Hong Kong in 1990 and 1993 respectively. In 1994, he joined the Department of Electronics Engineering, City University of Hong Kong, and is currently a chair professor and the associate head. From January to June 2006, he was a visiting professor at the Department of Electronics Engineering, the Pennsylvania State University, USA. His research interest includes antenna designs and electromagnetic theory. Professor Leong received the International Union of Radio Science Young Scientist Awards in Japan and Russia in 1993 and 1995 respectively. He received the City University Research Excellence Award 2013 and the Departmental Outstanding Teachers Award in 2005, 2010, and 2011. He also received the highly prestigious Higher Education Outstanding Scientific Research Output Award of the Ministry of Education, China, in 2016. He was the chair of the IEEE Antenna and Propagation and IEEE Microwave Theory and Techniques Hong Kong Joint Chapters for 2006 and 2007. He was the technical program chair of 2008 Asia Pacific Microwave Conference, Hong Kong, and the technical program co-chair of 2006 IEEE 10CON Hong Kong. He was a guest editor of IET Microwave Antenna and Propagation. He served as associate editor for the IEEE Antennas and Wireless Propagation Letter. He was also an associate editor for the IEEE Transactions on Antennas and Propagation, and received Transactions Commandant Certificate twice in 2009 and 10 for his exceptional performance. He was the editor-in-chief of the Transactions from 2013 to 2016, being the first appointed from Asia since the journal was founded in 1952. He was a distinguished lecturer for the IEEE Antenna and Propagation Society and a member of the Antenna Propagation Distinguished Lecture Program Committee. He is a fellow of IEEE. Now, it is a wonderful things that such a great speaker is with us as a opening speaker for this first session. With this one, I invite Professor Liang to start the session.
Thank you, Chairman. I would like to share my PowerPoint first. So can I do the sharing now?
Just wait. I'm giving you the. Just yes. Now you can start sharing the screen.
Yeah. Can everybody see my PowerPoint?
Yeah. Okay. So
yeah.
Visible.
Okay. First of all, I would like to thank Dr. Khan to invite me to join this meaningful event. I am KW Lang, or you can call me Ben Lang, from City University of Hong Kong. Today, I'm going to share with the audience the glass antenna work of my research team. Okay, this is the outline of my presentation. To begin, I will briefly discuss 2D transparent antenna, followed by the 3D transparent antenna, which is the glass dielectric resonator antenna. Okay, the 2D transparent antenna first. 2D transparent antenna is based on the theory of microstrip antenna. It uses meshed conductors or transparent conductors on acrylic or glass substrates. They can be used to integrate with planar clear substrates such as window glass or with solar cells. I will discuss transparent antenna using meshed conductor first. The working principle is very easy to understand. It's transparent because optical signal can pass through the opening, and it can be used as an antenna because microwave signal can be transmitted or received by the conductor. However, because of the meshed conductor, it is not fully transparent. Now, this is the first transparent antenna proposed by Wu and Ito in 1992 in this conference paper. It is a microstrip antenna, and the microstrip antenna and the ground plane were made with parallel wires. So you can see this is a patch. You can see parallel wires, and at the bottom of the glass substrate, they also use wires here. You see many wires for the ground plane. The wires are silver plate copper of cross section 0.2 by 0.1 square millimeter. And they use glass substrate as shown here. Now this is the main search bandwidth. It is about 1.5%. This is a typical bandwidth of a conventional simplex microstrip antenna. This is the radiation pattern. We have the broadside radiation patterns obtained for both the E-plane and H-plane as expected, because it is a simple conventional microstrip antenna. It has a front-to-back ratio of about 9 dB, and its cross-polarized level is about, less than -13 dB in the broadside direction. Here, this is the broadside direction, because the ground is along this y-axis. Now, this is the main search antenna gain of this transparent microstrip antenna at 925 megahertz. It is 2.5 dBd. D here means the gain relative to a standard dipole antenna, which is 2.15 dBi. That means the gain of this microstrip antenna is about 4.7 dBi, which is obviously much lower than a conventional microstrip antenna. It is because it is a mass grid microstrip antenna, not a solid metal microstrip antenna. Therefore, it will sacrifice the antenna gain. Okay, next, I will discuss the transparent antenna using transparent conductor. Now, this is the first transparent microstrip antenna proposed by Simons and Lee in 1997. They have presented two transparent antennas. The first one is that they have a silver-coated polyester film, which is conducting and transparent as the patch. And they also use AGHT for the ground. And they use the glass as the supporter so that the entire structure is transparent. And they use the transparency film as the substrate of the patch antenna. Now, the second structure is shown here. Again, they use transparent conducting film for the patch. However, in this case, they use aluminum ground plane, and therefore the entire structure is not transparent. For the substrate, they also use the transparency film as shown here. Now, these are the parameters of their designs. They use the idea of transparent conductive material. Normally, we call it TCO. TCO was found since 1950s. Since then, it has been quickly developed over the past decades. They have many different applications, including paper-thin LCD, plasma, touchscreen monitors on ATMs, etc. There are three common TCOs. The first one is indium tin oxide, ITO. The second one is the silver-coated polyester film, AGHT, and the fluorine-doped tin oxide, FTO. These are pictures of ITO, FTO, AGHT from the internet. Now, this slide discusses about the surface resistance of using the ITO film. The surface resistance is given by this, which is inversely proportional to the free electron density and electron mobility and the electron charge and also the film thickness. Now here we can see that for a given electron mobility, if we want to have a very high transparency, say the red dot or red star, the transparency is 90%, but the efficiency is pretty low. In this case, it is less than 5%. Now for the green star, the transparency is decreased from 90% to 80%. But then the efficiency will be increased. It's now above 10%. If we further sacrifice the transparency to 70%, this star, and the efficiency will further be increased to about 20%. Now, for different electron mobility, we have different efficiencies. But in each case, we have the higher the transparency, the lower the efficiency. Okay, this table summarizes the information that our team has found from these two references. For ITO, if we have a higher transparency, then the efficiency is only 32% for 90% transparency. If the transparency is decreased to 80%, then the efficiency will increase to 50%. And this is the surface resistance. Now, the cost of ITO is relatively high as compared with FTO and HHT. As you can see, the cost for FTO and HHT. However, although their prices are lower, their performance is not as good as ITO. This can be seen easily when comparing this transparency for ITO and this transparency for FTO. They have about the same transparency, but you see the efficiency is much lower. And for silver coat polyester film, there are two kinds of this film, HHT-4 and AGHT-8. AGHT-8 has a higher transparency, but the efficiency is lower. We don't have the exact figure from these two papers, but because its transparency is higher, then its efficiency will be sacrificed. So this is the surface resistance of this HHT. Now we have a rough idea about the TCO materials. This is a transparent antenna done by this research group. This is a monopole antenna. We can see the transparent conducting film here. It is ITO film. Okay, next I'm going to discuss a very interesting design by this research group. Now, this paper was published in AWPL, Antennas and Wireless Propagation Letters, in 2008. This is a coplanar patch. There's the other half, but because of the simulation efficiency, they only consider half in their model, but they can simulate the result for the entire coplanar patch because of the symmetry of the structure. Now, this is the current distribution of the coplanar patch. Now, in this current distribution, it is simulated for using copper patch and copper ground. We can see that the current of the patch and the current on the ground highly concentrate around the edge of the coplanar patch. Now, if we replace the copper by AGHT, we can see that the current on the patch and the current on the ground are decreased significantly. From this much decreased current, we can foresee that its antenna performance will be far below than this one. Now, that research group proposed a very clever and interesting method that, because they observed that the current only concentrate along the edge of the patch and the ground near the patch. Therefore, they put a highly conductive material around the edge of the patch and also around the edge of the ground, which is close to the patch. Now, by doing so, they will sacrifice the transparency because this is highly conductive material. However, because this is only a very small area, therefore, the transparency is not sacrificed that much, but the efficiency can be improved a lot because the current just concentrate around this small area. Now, this is the efficiency. Now, without using the highly conductive material around the edge, the dotted line here is the efficiency. You can see that basically it is below 40%. And then this solid line is the copper plate, copper case. They use the conventional copper for the patch and the ground. And we can see that the efficiency is very high. It's close to 100%. Now, this result is based on this result, but they put the highly conductive material around the edge with the width given by 0.1 millimeter, you see here. Then the efficiency is increased significantly. And if they further increase the width of the highly conductive material to 0.5 millimeter, so this line, and the efficiency will further increase. And finally, they increase the width to 1 millimeter. So this red line. Now, the efficiency is further increased to about 60%. Now, they didn't further increase the width of the highly conductive material because if you increase the width too much, then it will sacrifice the transparency of the antenna significantly. So it needs to have a compromise between the efficiency and the transparency. They also tried to find an effective surface resistance for this case. And they found that the equivalent surface conductance is 0.4 ohms per square unit area. Now, this is a very interesting result because they have a very good compromise between the transparency and the efficiency. This paper is an excellent paper, and they was awarded the AWPL Paper Prize for the papers published in year 2008. So you can see that the contribution is very significant and is widely recognized by the society. Now, they increased the efficiency from less than 40% to about 70%, and they won the best paper prize. And you can, from this, you can see that it is not easy to increase the efficiency of a transparent antenna. Now, the question is it possible to have a highly transparent antenna and yet we have a very high efficiency? Is it possible? Now, the answer is yes, it is possible. It is based on the theory of dielectric resonator antenna. Now, the DRA is an antenna that makes use of a radiating mode of a DR. It's a three-dimensional device of any shape. So all shapes of DR can be used as an antenna. For example, we can be hemispherical, cylindrical, rectangular, triangular, or any other shapes. So the shape of a DRA does not change its basic characteristic. The resonant frequency of the DRA is determined by its dimensions and also dielectric constants. These are two photos showing some samples of the DRA. You can see very high profile, low profile, circular, rectangular, triangular and rectangular, half split, quarter split, and hemisphere. So you can use whatever shape that you want. Okay, here I would like to give all of you a friendly reminder that the shape does not change the basic characteristics of DRA. Now, please put this in your mind because we will use this fact later in this seminar. Okay, now, dielectric resonator antenna is made of dielectric material. Now, glass is also a dielectric material. So the question is, can glass be used as a dielectric material for DRA? Okay, before we answer this question, let's see the well-known fact that the refractive index of glass is about 1.5 and its dielectric constant is 2.25. You square 1.5 and then you will obtain the dielectric constant. Now, this dielectric constant is too low for designs of DRAs. And that's why, since 1983, the proposal of DRA by Professor Stewart Long, no glass DRA has been found until this invention from my research team in about 2008. So there are about 3 decades with no invention of glass antenna. I believe this is a major reason that the dielectric constant is very low for glass, and therefore it is not a good idea to use glass for DRA design. However, there is something very important that has been overlooked for many years. Now, before I move to the next slide, I would like to ask you a question. We all know that the refractive index of glass is 1.5, but when do we have this knowledge? We have this knowledge when we were in high school studying the properties of light, about the reflection, diffraction, etc. When we study the light property, we know that the refractive index of glass is 1.5. However, we are now talking about microwave antenna. For microwave antenna, the frequency is 10 to the power 9 hertz. But for light, the frequency is 10 to the power 14 hertz. Now you can see that the microwave frequency and the light frequency has a very big difference from each other. The difference is as large as 5 order. Now, with this big difference in frequency, many things can happen that we overlooked for many years. Therefore, we measure the dielectric constant of glass at microwave frequency. Now, this is the measured dielectric constant of our Pyrex glass or K9 glass by using this dielectric material measurement set from Agilent. We found that its dielectric constant is about 6.8 instead of this 2.25 that was expected by many people. Now, with this 6.8 value, it is high enough to design very good dielectric resonator antennas. Now, when our research team found this result, we were very excited, but sometimes things are too good to be true. Therefore, we do some verification to confirm that our measurement is correct. Therefore, we measure the dielectric constant of air using the same setup, and we found that it is about 1. This is correct. And we also measure the dielectric constant of Teflon. As you can see here, is about 2.1, which is also correct. This verifies that our measurement for glass is also correct. And with this value, we can have many new designs. These are 2 pieces of glass DRA. Okay, the first application of glass DRA is for optical application. Here we have a transparent hemispherical DRA and this is a conformal excitation strip. Now the red one is the solar cell panel. So this is the top view, this is the solar cell panel, and this is the DRA. Now we use the conformal strip to excite the transparent DRA. Now the DRA serves as the light focusing lens for the solar cell panel. Now this is also a focusing lens. So for microwave frequency, it's an antenna, but for optical frequency, it is a lens that focuses the light into the DRA and then exposed onto this solar cell panel. Now this DRA also served as the underlaid protector. It is a protector for this underlaid solar cell panel. And therefore, we have a very compact design. We only use a single footprint to contain both the solar cell panel and the antenna. Now this is the experiment. I removed the DRA, put it here to see the solar cell panel clearly. And this wire and this wire are the output of the solar cell panel. These are the parameters of this DRA and the substrate. Now this is the actual configuration. The DRA is placed above the solar cell panel. First, we examine the antenna characteristic. We do the measurement and simulation for the return loss and input impedance. And we find that the agreement between simulation and measurement is reasonable. For frequency, the measured value is 1.94 gigahertz. The simulated value is 1.89 gigahertz. The error is less than 3%, which is acceptable. And the measured bandwidth is 16.5%, whereas the simulated bandwidth is 22.8%. But if we see the agreement about the trend of the curve, we can see that the agreement is acceptable. This is the antenna gain. The gain is about 5.3 dBi. So these are the radiation patterns in the E plane and in the H plane. We can see the familiar broadside radiation patterns of the fundamental mode of the hemispherical DRA, meaning that the gas DRA operates as a normal hemispherical DRA. Now, in the broadside direction, so this is the broadside direction, the co-polarized field is larger than the cross-polarized field by 22 dB. Okay, next, we examine the optical part. We use a prism to focus the light, into the converse. Here is the light source. We use this lens to convert this beam into the parallel light. Now, this configuration has a theta equal to 0. And then we change the value of theta, but we keep this incident angle unchanged. And therefore, the value of theta will increase from 0 to larger values. Here is the rotator so that we can change the incident angle onto the DRA. Now we use a laser source. Wavelength is 488 nanometer. The light power is 130 milliwatt. Now this is the result for the voltage, and this is the result for the current. Now when theta is 0, that means it is exactly this configuration. It is normal incidence. We can see that the solid line, which is with the hemispherical DRA, that means we have the focusing length. The output voltage is higher than that without the lens. But as we increase the theta up to a certain point, in this case about 30 degrees, then the the voltage with DRA will decrease because of the diverging effect of the lens. Similarly, we have similar result, a similar trend for the current. At around 30 degrees, we have the current without the lens being higher than the current with the lens. But before this angle, the current with the lens is higher than that without the lens. And therefore, for theta less than 30 degrees, we can have a higher solar cell output power. Now, if someone wants to have the glass DRA, but he or she doesn't want to have the focusing effect, then a rectangular glass DRA can be used. In this case, we have a conventional antenna performance for DRA. Again, basis pattern similar to the hemispherical one because, as I said many times, the shape of the DRA does not change the basic characteristics. Now, here we can see that the result with DRA and the result without the DRA are much closer to each other than in the hemispherical shape. Although with the DRA, the output voltage and output current will decrease as you increase the illumination angle theta, but the difference is much less than in the hemispherical DRA case. Okay, next, let's discuss the transparent DRA used as a decoration. Now, DRA can be of any shape. Can it be made like a swan? So that's why I mentioned this point again and again. If it is really possible to be of any shape, then is it possible to use a swan shape for the glass DRA? The answer is yes. Now, if this is positive, then it leads to probably the most beautiful antenna in the world. This one. This is the glass swan antenna. And this glass swan is nothing special. It is only a decoration for home or office. We bought it from the commercial market for decoration. Although people have not thought that it can be used as an antenna. Now, this work was published in this paper in Proceedings of the IEEE by my research group. Now, with this aesthetic transparent antenna, we can have office decoration using an antenna. It can save space because we don't need separate space, one for antenna and one for decoration. Now we can use the same place for antenna and decoration. Now we have one more research direction. We now turn antennas into artworks. Also, it is a very excellent invisible antennas. Invisible in the sense that people would not know that it's an antenna. It doesn't mean that people cannot see it. We can see it, but we did not know that it's an antenna. Now, this is not only a gimmick, but it has a very practical application. Let me share with you a true story. About 18 years ago, in a Hong Kong airport, the handling of baggages and luggages were done by a subcontract company. At that time, Hong Kong already used RFID for handling baggages and luggages. So there are workers working under RFID radiation during their office hour. or working hour. Okay, one day, one man and one woman of the company made a complaint to the management of the company. They complained that both of them got cancer at the same time. So it should not be coincidence, because both of them got this health problem around the same time. And they strongly believe that it is because of the RFID radiation. And therefore, they asked the company to compensate for that. And of course, the company refused to do the compensation. And then the two staff members complained it to the court. They sued the company. Now, I'm not an expert on microwave biological effects, and therefore I don't want to make any comment whether their cancers were caused by the RFID radiation or not. But what I can tell is that it has been clinically proved that anxiety can cause one person to have cancer much easier. Now, from the complaint of the two staff members, it's obvious that they got a high anxiety for working under the RFID radiation. So even if the RFID radiation is harmless, because of their anxiety, it is easier for them to get cancers than other people. But if they use this gas worm antenna for their workplace, they don't know that it is an antenna. Conversely, they see a beautiful decoration and they will feel very relaxed, and it is more difficult for them to get cancer. And therefore, it has a very practical application. These are the dimensions of the swarm. This is the ground plane, and here is the coupling slot. The swarm is put on this coupling slot for the antenna. Now, this is the Mansard reflection coefficient. The resonant frequency is about 1.83 gigahertz, and the impedance bandwidth is very wide, 31.6%. Now, this wide bandwidth is due to the air gap. You see the air gap here between the wings of the swarm. So the air gap is formed naturally because of the two wings. Okay, people may argue that the resonance is actually caused by the slot instead of the swarm. So let's see this result. If we change the slot length, then the frequencies should change linearly with the slot length. However, we can see that here, the resonant frequency remains almost unchanged. This is one verification. The second one is that we can track the antenna gain. Now the antenna gain is as high as 7.4 dBi. But for slot antenna, even if you have a glass loading or dielectric loading, the gain is normally around 3 to 5 dBi. Now this high antenna gain is consistent with the conventional antenna gain range, and it is much higher than the gain of the slot or dielectric loader slot. It further verifies that the antenna operation is due to the swarm resonance instead of the slot resonance. Okay, these are the radiation patterns of this gas swarm antenna. Again, we have the ball site radiation pattern as expected. Okay, we applied this gas swarm antenna into a wireless video system. Here we have a DVD player. We place the DVD and the audio and video signal is output here, and then to this modulator to modulate their frequency to 2.4 gigahertz to here. And then the modulator video and audio signal is transmitted to this receiving monopole antenna, and then demodulation. And then the video and audio signal are sent to this TV. So what we see from the TV is actually the content being played by the DVD player. Okay, now this is the ground plane, and the other side is a microstrip and microstrip line. Okay, let's see a video. Okay, now what we see here is actually the content of DVD being played. If we remove the swarm, you see the video signal is lost because the antenna is not there. If we put it back, the video resumes. Now you see it coincident, or let's try again. We remove it, the video is lost. If we put it back, it resumes. So it demonstrates that it is a real antenna. We have built a HFSS model for the swarm, and we have compared the simulated and measured result. The agreement is pretty good. Now, the shape is not important. Therefore, we try the apple. These are the parameters of the apple. We have the ball side radiation pattern as expected. And we have also tried big band glass antenna. In this case, we have a probe penetrate into the glass antenna at the center. And therefore, in this case, it will excite the only directional mode of the antenna instead of the ball side mode. This is the probe. And these are the parameters of the antenna. Is the height of the big band glass and the square bottom. Here, the square bottom. Okay, let me take a piece of pointer. Okay, this is the ground plane size and the coaxial probe size. Now, we have very good matching for this antenna. The resonant frequency is about 2.89 gigahertz. This is the bandwidth. We have a wide bandwidth because we have more than one resonant modes merged together. Okay, we have this, the fundamental mode of the DRA. It is only directional radiation pattern. This is the elevation plane. This is the horizontal plane. And then we measure the pattern at higher frequency. The result is similar. And then we have a higher order DRA mode. Because of this high order mode, we have a very wide impedance bandwidth. Now, the radiation pattern is not the same as before because this is a high order mode, but still we can obtain an omnidirectional radiation pattern. Okay, next, we investigate using DRA, glass DRA, as a light cover. Now, we can have a hollow glass DRA and insert the light source into the hollow region. And therefore, this DRA simultaneously functions as a cover of the light source. Now, with this idea, we can have very wide application. Okay, first of all, indoor antennas have been widely found in modern buildings, especially for commercial mall. They have many indoor antennas. And also for all buildings, there must be light source, and then we will have light cover. Now, we can combine the lighting system and the antenna system into one, and therefore we can save space. And also, it saves cost and work because the lighting system and the antenna system can be installed in one go. And also, it is an excellent invisible antenna to avoid uneasy feeling of radiation of people. Okay, this is a dual band antenna for Wi-Fi application. It is a dual band that operates at 2.4 gigahertz and also 5.8 gigahertz, which are Wi-Fi frequencies. These are the parameters of our hollow glass hemispherical DRA. Okay, these are the results. We have the simulation without the LED, and then we have measurement without the LED, and also the measurement with LED. Now, from this result, we can see that this measurement and this measurement almost overlapped. It means that the effect of the LED is negligibly small. Therefore, in designing the antenna, we can ignore the LEDs. Now we can see the 2.4 gigahertz resonance and now also 5.8 gigahertz resonance for Wi-Fi frequencies. Here, around 4.7 gigahertz, there's another DRA mode, TE311. This mode is not wanted, and we can use a filter to filter this mode out. Okay, for the first mode, 2.4 gigahertz, the bandwidth is about 21%. For the second band, it is about 10%. Both bandwidths are much wider than 3% of Wi-Fi frequency bandwidth. Okay, these are the animation for our fundamental mode, the first higher order mode. They have all size radiation patterns for the fundamental mode and also high order mode. Because here, we can see that this is 111 mode, this is 112 mode. So this mode and this mode actually come from the same TE mode family, and therefore their radiation patterns are similar to each other, except that the higher the order of the mode, then the smaller the beamwidth of the radiation pattern. Okay, these are the antenna gain results for simulation and measurement. Again, for the measurement, the result with LED and that without LED are basically identical. And the agreement between simulation and measurement is pretty good. Without LED, the maximum lower gain is 5.26 dBi, with LED is 5.43. So the difference is very small. And for upper band here, without LED is about 7 dBi, with LED 6.76 dBi. Again, the difference is only about 0.3 dB, very small. Okay, next, we design another glass covered DRA. This is a glass. Here we have a hollow region for the accommodation of the light source. Here we have the feeding probe. This is the top view. This is the real glass antenna. Here is the bottom. We see the hollow region for putting the LEDs. And here is the hole for the penetration of the probe. This is bottom face. This is the perspective view. Now, these are the 4 LEDs put inside. Now, here we have the measured and simulated return loss. This is due to the probe mode. This is due to the DRA-TM mode. Again, agreement between the simulation and measurement is pretty good. The measured bandwidth is about 29%. This is the omnidirectional mode because here the probe is fed at the center. Therefore, due to the symmetry, it can only excite omnidirectional radiation mode. This is the antenna gain. At the frequency we are concerned with, 2.4 gigahertz, the gain is about 1.8 dBi. Now, this is reasonable antenna gain for an omnidirectional antenna. Okay, next, we consider the CP antenna designs. CP antennas are useful to tackle the Faraday effect, fading effect, and also it decreases the alignment requirement between the transmitter and receiver antennas. Now, to change the linear polarized field to circularly polarized field, we can put a strip on each side of the side wall of this rectangular DRA. So we have another one behind this and the fourth one behind this. So there are 4 strips in total to change the linear polarized field into circularly polarized field. However, with this copper strip, the antenna is not fully transparent. So we can use ITO coated glass strip to obtain a conducting strip to model the copper strip. And on the other hand, it is transparent. Now, the good of this design is that we can have a transparent antenna, but the drawback is that it is lossy due to the ITO coating because its conductivity is much less than that of the copper. So the efficiency will be reduced. Now with this ITO coated glass strip, the entire antenna is transparent. Okay, we turn on the light, it is transparent. You can see the light passing through the strip. However, the efficiency is sacrificed. With copper patch, the efficiency is close to 90% for the peak value. But for the ITO glass strip, the efficiency is only around 70% or less. So this is the cost that we need to pay to have a fully transparent antenna for the CP design. This is another design. Okay, next, I also applied this antenna to the wireless antenna setup here. It is the same setup, except the glass worm is now replaced by the table lamp. Okay, let's see the table lamp here. This is the glass antenna. Here we have 3 super bright LEDs. And it is so bright that we cannot look at it directly. Otherwise, your eye could be damaged. Now at the bottom is the biasing circuit for the lamp and also for the modulator. This is the modulator. It is now embedded inside this base of the table lamp. Okay, let's see a demo for this. Okay, again, okay, now let's turn on the light. You can still see the video. Turn off the light. You can still see the video. Okay, just now you see some flickering effect on the screen when the switch is turned on and turned off. It is because of the biasing circuit. We didn't design the biasing circuit seriously. We just want to provide some power to the LED and to the modulator. So this flickering effect can be avoided if we design the biasing circuit carefully. Okay, now let's remove the cover, and then we see the glass. We remove it, the video is lost because the antenna is not there. If we put it back, it resumes. Okay, if we turn on the light, it's still there. Turn off the light, again, the video is still there because the optical frequency and microwave frequency are too far away from each other. So microwave signal and optical signal do not affect each other. Okay, this finished the demonstration. Okay, this is the front page of a newspaper in Hong Kong in year 2011, August 13. Now, what is this news report about? Here, you can see, perhaps I change back to content. Okay, here, this stuff is a repeater of the mobile phone system, the base station, repeater of base station. And then there is a citizen in Hong Kong sued the company to the court, saying that this repeater affects the appearance of the city. And also, it makes people feel uneasy to have the radiator so close to people walking in the street. Now, people complain about this because people can see it. If people cannot see it, then nobody will notice the antenna, and therefore there will be no complaints. And their psychological state would be better. Therefore, what about if we use the glass antenna, the light cover for the light switch, we put here? Then no people will complain that we put an antenna here. Or if we put it in the traffic lamp, we put it here, then again, I don't think people will complain that you have an antenna here because they don't know it. So this is a solution to the problem. Okay, this concludes my presentation. We have discussed the 2D transparent antenna, which is based on the patch antenna theory. It used meshed or transparent conductors for the patch and the ground plane. And then we introduced 3D transparent antenna, which is actually glass DRA for different applications. It can be focusing lens, decoration, or light cover. And in fact, there are many other applications which are limited by our imagination only. Thank you very much.
Thank you, Professor Ben, for a wonderful and comprehensive first session of this event. Now I need to forward some queries from the participant sides because participants are on other platform, that is YouTube link. The first query from the participant is,
so I pass the time back to the chairman.
Okay, what are the fabrication challenges of 3D glass antennas? The first query from participant side is, what are the fabrication challenges of 3D glass antennas? Fabrication challenges.
Oh, okay. Thank you very much for your question. The glass is not tailor-made glass. It is only Pyrex glass. Pyrex. It is very common. So the source of the glass is not a problem, and it's very cheap. The cost is very low. And the glass can be machined by the modern machining tools. In fact, we send our glass to a workshop and they do it for us. We can make a hollow size, a hollow region for a glass. We can machine it to and hemispherical shape, and also rectangular shape or other shape. So the fabrication is not a problem at all.
Okay. And now, if for the same performance, if I design a traditional DRA and glass DRA, which one will have a cost, more cost? Which one is costly?
I would say glass is actually cheaper, because glass actually is very cheap. Glass, especially if you are in mass production, the cost is very low. It can be much lower than your dielectric, ceramic, or composite material.
Okay. Now last query, that how to improve the glass antenna efficiency. Would you suggest some method how we will improve the efficiency of glass antenna?
Now for glass antenna, in fact, we haven't sacrificed the efficiency as long as the frequency is below 8 or 10 gigahertz. We did a measurement for the loss tangent of the glass. When it is less than 8 gigahertz, the loss tangent is about 0.05. So it is not high at all. If the frequency is very high, then we may need some very high quality glass. For high quality glass, it may have low loss too, at millimeter wave frequency or even higher. When I said it is lower than 8 gigahertz, I refer to very cheap glass.
Okay. With this, Dr. Surendra Pal, sir, would you like to raise some query or some discussion on this talk? Because your microphone is on.
No, thanks. I wish to thank the speaker.
Oh,
He has
okay,
opened
okay.
a new avenue for our researchers.
Yeah. Thank you, sir. Thank you, Professor Ben, for this wonderful talk. Yes, with this, we would like to say thank you and bye-bye to you, because it is, I think, too much late in your region. I think around 11:30 p.m.
It is about 11 p.m.
Okay. Now enjoy your dinner and take rest.
Okay, thank you.
Thank you very much once
Thank you.
again. Okay, sir. Bye.
Bye-bye.
Okay, sir. Is the screen visible now? Is the screen visible to the participants?
Yes.
Okay, thank you. Now, as a guest, as a second speaker of the day, Dr. Surendra Pal, distinguished scientist from ISRO Satellite Center, Bengaluru, India, is already joined us. So, for inviting him for the talk, I would like to introduce him before the participants. Dr. Surendra Pal, an alumnus of BITS Pilani, India and ISC Bengaluru, is presently holding DRDO Dr. D.S. Kothari Chair in the former Vice Chancellor of Defense Institute of Advanced Technologies, Pune, President of IET 2012 to 2014. He was also the Program Director and founder of Indian Satellite Navigation Program, NAVIC, Indian Regional Navigational Satellite System, Program Director Gagan, Professor Satish Dhawan, Professor, Senior Advisor Satellite Navigation ISRO, and Aditya Birla Chair, BKBIT Pilani. Dr. Pal was responsible for starting microwave antennas, microwave and satellite navigation activities at ISRO Satellite Center from inception. He was consultant to ITU International Telecom Union for defining rural African satellite communication and on the GNSS panel of UN Office for Outer Space. He had developed mobile satellite antennas for ICON in Marsat, UK, and he was also consultant at NTU Singapore on X satellite. Dr. Pal is a distinguished fellow of IEEE, fellow of IEEE USA, fellow of IET, fellow of Indian National Academy of Engineers, fellow of National Academy of Sciences, and fellow of IET UK, fellow of VEDA, fellow of ATMS. Dr. Pal has received more than 24 national and international awards, which includes Judith Resnick Award from IEEE. He is the first person to get the award from East of France. Dr. Pal is IEEE DLT Distinguished Lecturer, INA Distinguished Visiting Professor. He is also Honorary Professor of MIT University, Noida. He also visited under IEEE DLT program several universities in USA, UK, South Africa, Australia, Malaysia, and Singapore. Dr. Pal's expertise is satellite communication, RF microwave, digital communication, radars, antennas, and global navigation satellite system. It is an honor for me as well as for all of us that this evening Dr. Pal is with us for delivering the talk on a topic importance of polarization and noise in antenna system. Sir, may I now request you, sir, to start the session?
I think you have to allow me to share my
Yes, sir.
screen.
Yes, sir. I have allowed you, sir. You can share the screen on.
No, I'm not able to get it.
Sir, bottom right side, there will be one icon, present now.
Yeah, I ticked it.
Yes.
Then your
Then-
entire screen.
Yes, entire screen. Then click on that. Then share
share.
option will come.
I
Share
did it.
icon.
I did it.
Okay. No, sir, you have not done that one because still it is blank. You do it again, sir.
Okay. Entire screen. Share.
Yes.
No, it's not coming. Bear with me for I'll call my son, who is an expert on these things.
Okay. Sir.
जल्दी आओ यार, मैं इसकी शेयर नहीं कर पा रहा इसकी. Okay, I think we will start audio. I mean,
Yes, sir.
going to come another
You are-
couple of minutes.
Okay.
Professor Taimur Khan, my dear friend Dr. Ashok Dey, the director of NIT, other distinguished faculty members, distinguished speakers, students. It's really great matter of pleasure for me to talk to you. I mean, I wanted always to visit Silchar because one of my relatives had a lot of tea gardens at that site. But I mean, the pandemic did not allow anybody to go. Okay. Now, your topic was is very interesting, and this Dr. Taimur told me. Share my screen.
Yeah.
Yes. Share.
A window.
Yeah.
Share. Being shared.
1 minute.
Okay.
Okay, is it visible?
Yes. Is it visible?
Okay. So, I mean, I wish to speak couple of, I mean, I did tell Dr. Taimur that I am not the person who has worked on dielectric resonators. I worked in somewhere in 80s when we wanted to make a small antenna and the oscillators, filters using the dielectric resonators. We did not find dielectric resonators, the stability with respect to temperature and vacuum was very poor. And of course, we did not try as an antenna. But when we studied that time, later on also, when I was a consultant to defense, see, dielectric resonator antennas hold a very big opportunity for all of us. They have got capability of miniaturization, compact design, circular polarization, multi-band, and wideband polarization agility. Now, polarization agility is one thing which we can't get in most of the other antennas, which we can get in dielectric antennas. There are new areas which we should do it. If the earlier speaker, Dr. Ben Lung, can work on K9 glass, which is plentifully available in India also, perhaps researchers can do much better than that. A theory can be developed. I developed a theory on dielectric antenna, particularly a sphere, somewhere in 1978 to 84. So those things concept can always be used. Now, you see, it can provide enhanced gain, finite ground plane effects, tunable dielectric resonator antenna, reconfigurable antennas, ultra wideband design. Okay, and it can give a antenna and resonators. The shape could be anything, conical, cylinder, plate, etc. Now, since earlier speaker said we can use the K9 glass, so we can also use those things. Although he is used in the lower frequencies, but dielectric resonator antennas can be used from 55 megahertz to 94 gigahertz. So, whosoever is listening, particularly for researchers from NIT Silchar, you got a good opportunity, and if you need it, I can arrange through ISRO, from my some of the good office, a better glass whose losses are quite less, both in optical as well as in RF domain. Circular polarization design by multi-feed design is possible in this case with a lot of miniaturization, which we usually do with microstrip transmission lines. Polarization agility by 2 feeds. We don't get a polarization agility so much in our conventional antennas, which we can get in dielectric resonator antennas. And micro machine dielectric resonator antennas and dielectric resonators can, a combined system can be there. We can have a filter, we can oscillator, and also the antenna. And the overall thing can get, in a very miniaturized shape with a good efficiency. The earlier speaker has shown efficiency of about 60 to 65%, and I think that sort of efficiency can be improved. Even if it's not improved, it's useful for many purposes. I would suggest for the researchers to
वो चलेगा
try these things for
query देख लो, you are not listening
5G.
you are not listening the query. Participant query. Who is taking that one?
Oh, shall I go ahead? Dr.
Yes,
Taimur,
sir.
can I go ahead?
Yes, sir. Please.
Okay. Now, what are the problems in dielectric antennas? If you use in a space or for a better communication, efficient communication, is there is a inherent noise in dielectric resonator antennas. Okay, and although it can have a circular polarization, but no study has been done with a very good cross polarization. If you can get a cross polarization of the order of 25 to 30 dB, these things can be used even on ground stations. We have used simple Teflons for ground station feeds at S-band and all 11 meters antenna, etc., have got the same feeds using the Teflon dielectric antenna. When we developed it, the commercial one was costing I think it was around $2,000. And the dielectric antenna, which we made in our laboratory, and later on it was commercialized. In our laboratory, it was 5,000 rupees, and when commercialized, we were paying for 15,000 rupees, and ECIL uses those things very well. Now, with these few comments, I'm going to talk something. There are a lot of things which one can talk on the antennas, and I think I have worked for almost more than a century in this field, half a century in this field, so I can talk many things. But what I found that majority of the researchers do not give any importance, or most of them don't understand, PhD students, about polarization, importance of polarization and noise in the antenna system. I have seen a PhD thesis of a very reputed institute, guided by a very reputed academician. I will not name him because he's a good friend of mine. The antennas, there is a microstrip antenna, and I asked him in the Viva, what is your polarization of the antenna? No, my antenna is a polarization less. So a person, electromagnetics is a vector. So any vector field has to have a polarization. So that concept should be taught to the students very well. And with respect to this, I'm going to talk a little bit about this thing. Dr. Taimur, how much time have I got? Hello.
Yes, sir. Sir,
How much time?
35, maximum 40 minutes, sir.
Okay, so I can finish it by 9 o'clock or earlier?
Yeah. 9 o'clock, sir.
Okay, so IEEE definition is not the conventional definitions which we have been taught into the cross book and others. A means for radiating or receiving antenna radio waves. For antenna technologies, it's an interface between the free space and RF circuit devices. Usually it is reciprocal in function. When we were students it was taught, but with the advent of active antennas, smart antennas, phased arrays, adaptive antennas, reciprocity does not get uniquely associated with the system. Antennas differ in several aspects from each other depending on the applications. Radiation pattern varies from omnidirectional antennas to highly directional, can be fixed or reconfigurable. Let me add it here, and that also will complement the earlier speaker's thing, Pen Lung, that antenna technologist is like an artist. Okay, it's like a painter or an artist, and he can design any type of antenna as long as he can look into its efficiency, radiation pattern, polarization, and of course the feeding network. So antenna technology should not be bound by what has been taught into cross or other books. Those books are good for clearing your fundamentals, and they are good to pass the exams. If we were to follow the conventional antenna systems or designs by lambda by 2 or lambda by 4 and all those things, then Steve Jobs would have never created iPhone. Okay, I request the students to open a smart telephone and find out where is the antenna. So that's the thing. You can really make a very good antenna with different shapes. And the earlier speaker has talked about using the glass antennas, putting thing in which can be used for many purposes. Now, it should be designed to withstand the dynamic, mechanical, thermal stresses of the environment. It may be any environment. If possible, we should try to reduce its size, shape, and weight so that it does not interact with the other systems. For aerospace, both for air as well as the satellite, we use antennas for TTC, data transmission, communication, and inter-satellite links. Nowadays, satellites are like a antenna platform. If you have seen the NewsX Dragon, you will find that antennas are not visible, but they've got n number of antennas, including before they dock, they've got a monopulse comparator to check it where it's going. Then they've got the sensors, then they've got the laser tracker, and then finally they go and dock. Right? Antennas are omnidirectional antennas, shaped beam, sectorial beam, multi-beam, scanning array, adaptive array, beam reconfigurable antennas. Now let me ask the students, which is other field which gives you so much of flexibility to do research. For ground station antennas, we have got medium gain, sectorial gain, high gain with narrow beam, low gain, hemispherical coverage, sectorial gain, scanning arrays for radars, etc. So, what are the important parameters? I'll just touch upon it. Frequency of operation, radiation coverage requirements, polarization, bandwidth with respect to gain, return loss, polarization. All three are very important. You can't say my gain is 3 dB or 10 dB or 50 dB unless you define them with respect to return loss and polarization. Power handling, multipackaging, RF breakdown, EMC, EMI. These are very multipackaging in a very high vacuum. The multipackaging occurs, while RF breakdown occurs when there is a critical pressure, when 10⁻³ or so. That sort of thought. Isotropicity is a new parameter which defines, overall how far away it is from your isotropic antenna, which is a hypothetical antenna. Then mounting clearances should be there for sensors and other antennas, buildings, etc., size and mass, material degassing, degradation due to UV particles, impacts, and radiation environment. The earlier speaker talked about putting a thin uh, conducting sheet on the glass. We use such things for optical dichroic polarizers and other things, but there the degassing becomes a biggest problem. Body effects of the platform on the required radiation pattern becomes another thing, and the temperature limits. In space, we use from -180 to +150, vibrations, grounding scheme, etc. Another thing. So then orientation of an EM wave in space is there, and polarization of electromagnetic wave and receiving antenna is an important factor, and the E vector defines the polarization of that particular thing. Now, power transfer, which we usually say it is between antenna to antenna, that is a wrong concept. Power transfer problem is between wave and an antenna rather than between the two antennas. And in between the environment or the atmosphere or media, whatsoever you may call it, can change the polarization. Okay, so that's why that plays an important part. It can change the polarization in certain aspects. A circular polarization RSC can become LSC. Okay, a linear can become elliptical. So all those things have to be taken into account, and you have to study the medium in between. I'm giving an example. The medium in which wave travels can alter polarization of the wave as it appears at the aperture of the receiving antenna. See, rainwater. We always think the rainwater is like this droplet, but actually it's a ellipsoid. Okay, and when the electromagnetic wave goes, major axis and minor axis makes changes its polarization. So incidentally, the shape of the rain is nothing like that. What they think. This is the drop you get from dripping tap. In reality, main drop tends to be towards a sphere, but the force of the air on the base and also gravity makes it flatten. It becomes more of a ellipsoid. See, these are the, if you take, we have derived whole of our electromagnetic theory from the optical thing. And once Maxwell proved that electromagnetic radiation and light are same, after that, a lot of work was done in that one. But before all these things, still we work on device work, under the diffraction, Fraunhofer's diffraction, Fresnel's distance, all those things we work it. So here you see randomly polarized wave is there. You got a slit in the vertical direction. You get a vertical polarization. If you got a horizontal slit, you don't get anything. So this is an example which shows that how polarization becomes an important factor. This is a linear polarization where this direction of propagation is there, and the electric vector is always perpendicular to the direction of propagation. Okay, in one direction. That is, you can say it will be in a say x direction or y direction depending on whether how do you. And we call horizontal and vertical polarizations are nomenclatures on ground. Okay, but when we go into the space, these nomenclatures are no longer valid, but still we say that vertical polarization is along the north pole and horizontal polarization is along the equator. So if you take a circular polarization, here the electric vector will making a circle. And why you are somebody may say why it's going like not in one place? Because electromagnetic wave travels with time. If it's in one place, we get only E field or magnetic field. We don't get a propagating medium. So for propagating medium, so if you got electrical, then same thing that it's on the perpendicular to it, it makes a ellipsoid. So non-spherical raindrops, we have already talked about it. Drop size is 2, 4, 8. Axial ratio go on changing. This is an example which I am giving you. It can axial, and depending on the air, the wind, this can change. So the axial ratio again changes. So below 15 gigahertz, most of the depolarization comes from the differential phase shift, and above 15 gigahertz, most of the depolarization comes from the differential attenuation. So both the phase shift, the attenuations are more important. This one. This is an end view of an unpolarized light. This, you can see that they're randomly polarized. If you have got a slit in this direction, then we get a polarized light perpendicular to the direction of propagation. You see, here is unpolarized light. It has got both the components. You put a slit here, it will come only the vertical polarization. If you put a slit here, it will come the horizontal polarization. And since here is vertical, it will not come. And this property is used for making the polarizers, dichroic polarizers, etc. So this is another thing. A Faraday's rotator is an optical device that rotates the polarization of the light due to the Faraday effect. And this phenomena occurs in the atmosphere and the media also. So one should study very carefully. The Faraday rotator works because one polarization of the input light in a ferromagnetic resonance with the material, and which causes its phase velocity to be higher than the other. So depolarization occurs both from the phase shift as well as the attenuation. This is an example which you must have studied in the 12th or maybe in BSc. So, here is a tube, okay? It's a tube which is filled with the saturated sugar solution. You apply a light, go on changing by rotating it, and you get a different colors, because the random light, which has got all the wavelengths. So you see the different rotation is different for different wavelengths. There is a rotational dispersion. Different colors are seen along the tube, producing a spiral appearance. As the polarization is turned, the whole spiral rotates like a barber pole. So this is an example which perhaps electromagnetic students should be told that how importantly is the medium which changes our polarization. Okay. Now, in order to select a specific polarization of light, polarizers are used. Polarizers can be broadly divided: reflective, dichroic, and birefringent polarizers. Reflective polarizers are transmit the desired polarization while reflecting the rest. It's a wire grid polarization which we use in space. We have most of our systems are dual polarized, horizontal polarized, vertical. So if you put the horizontal grids, then it reflects horizontal polarization, but vertical it allows. And vertical grids is allow the horizontal polarization. That's the simple principle. Because to cut short the time, I'm going ahead. So dichroic polarization absorb a specific polarization of light, transmitting the rest. Modern nanoparticles polarizations are dichroic polarizations, and NIT Silchar is very near to IIT Guwahati. I suggest the researchers can go there. They've got a nanotechnology center, and you can work with them to make a dichroic polarizers. It's a very good topic for PhD. I have visited those labs. Birefringent polarizers rely on the dependence of the refractive index of the polarization of light. Different polarizations will reflect at different angles, and this can be used to select certain polarization to light. The earlier speaker, he has got a K9, but with different directions. There may be a little bit of anisotropicity, so the polarization will change it. And I think that's a good topic to do a research. Now, color of the light wave changes when it passes through certain media. The 19th century French mathematician Poincaré showed that it is advantageous in certain problems in optics to associate the polarization state of a wave with position on the surface of a sphere. And Deschamps adopted the Poincaré sphere to radio waves, because when I'm talking about the optics, optical waves or light waves and the radio waves, they can be used interchangeably in this particular case. The Poincaré sphere, most of the researchers, most of the teachers don't explain it. Poincaré, because once in a PhD examination of a very reputed institute, IIT, I asked the researcher, do you know what is Poincaré sphere? Sir, I have never heard. I say, you got a smart telephone? Yes, sir. Google and find out what is Poincaré sphere. So Poincaré sphere provides a graphical aid in visualization and solving the polarization problem. Now, this is the Poincaré sphere. You see, you can represent any antenna polarization on this sphere. Now, along the you see, if it's North Pole, it's a right-hand circular polarization, okay? And if South Pole, it will be opposite left-hand circular polarization. If you go into the 45 degree, this will be linear polarization, but its orientation will be changing, okay? Like suppose here it's a vertical polarization, here it will be horizontal polarization. Here it's a elliptical, I mean, in one direction, it's 45 degree this direction, it will be opposite of 45 degree in this direction. So this shows that Poincare sphere is very important to us, and if you further extend it, your electromagnetic waves, when they reflect, they can also, depending on the angle of incidence, they can also change their polarization. Okay, and in certain cases, say suppose you are transmitting horizontal polarization, it comes horizontal polarization, but some certain cases by different orientations, both of the reflector and the uh, incident wave and incident angle, you can get even elliptical polarization. So this is another representation of the same thing you can find out. I mean, I'm just the Poincare sphere, and you can get the ellipse here. So linear polarization, as I have told, it's the this is the axis of transmission, propagation. So anything which goes perpendicular is a linear polarization. See, like and it of course it varies because electromagnetic waves is time varying. Like t is equal to 0, suppose its axis is t is equal to 1/85, it will be small in dimension. 1/4, it will be almost 0. Then t is equal to 3/855, it will go, and finally it goes this direction. So it will be oscillating from one direction to another direction in the same plane, or same along with the same line. So these are observed at the origin. The E field oscillates back and forth in magnitude, always directed along the x-axis, because the E field stays along with the line single distance. So this is called linearly polarized. Vertically polarized, horizontally polarized are nomenclatures on ground. If you are doing it, if you go into the space, I told you, vertically polarized is along the North Pole, and horizontally polarized is along the equator. A linearly polarized wave does not need to be along the horizontal or vertical polarization axis. For instance, a wave with E field constant to lie along the lines shown in figure 3 should be linearly polarized. This is a linearly polarized. Only thing, if you have got a dual polarized antenna, dual linearly polarized antenna in receiving, then you can always convert into two polarization. So for polarization diversity, we all in ground stations, even most of the places, you transmit a circular polarization or linear polarization, but you receive in dual polarization. And why from GPS signals are transmitted in the circular polarization, your ground station antenna is usually linear polarization, that is a handset, and you rotate it. That shows that you are trying to do the polarization matching. So locus of E field amplitude for a linearly polarized wave is given by this simple equation. Now you see circular polarization, you can find all directions, in this one. Only thing is that this will be varying with respect to time. In the case X and Y components are 90 degree out of phase, both spatially as well as the electrically phase. The field is observed at X, Y, Z equals 0, 0. Again, as before, the plot of the E field versus would appear as shown in these things. Now, the E field must have two orthogonal polarized perpendicular to each other, both spatially, that is 90 degree, and both phase wise also, there should be 90 degree out of phase. Now, if the wave is traveling out of the screen, the field is rotating in the counterclockwise direction and is said to be right hand circular polarization. You can also use your hand, put a finger towards next to the thumb. You can put the finger towards the direction of propagation, and the rest you bend it, and they will show you the direction of propagation. It's a very simple thing. Now the E field has two perpendicular components, okay, and that are out of phase by 90 degree, but are not equal magnitude. Then it becomes the elliptical polarization. You see it here. I'm just skipping it. This is elliptical polarization, and axial ratio of A and B is called the axial ratio. And this particular thing, you don't have to be very complicated system. By a rotating dipole, you can find it out. So ellipse has got a major axis, minor axis. The angle of the semi-major axis measured counterclockwise from the positive horizontal axis is the orientation phi of the EM wave. Any researcher, any PhD students, if he does all these things, at least in a half a chapter, it will increase the value to the his PhD thesis if he's working on antenna. Okay, that's my experience. Now, the degree to which the ellipse is oval is described by a sphere parameter and eccentricity or ellipticity called chi, which is arc 10 b by a, which can take values between -45 to degree 45. And when the components are in phase, the polarization is linear. Chi is equal to 0, chi is equal to pi by 2, chi is equal to 45 degree. You can get various things. I'm just skipping. So the power transfer problem is specified to be between a wave and antenna rather than two antennas. And mind it, the wave with whatsoever polarization it has got and whatsoever polarization the receiving antenna has got, that two polarization makes the difference for the total received power. So the wave produced by either a passive scatterer or an active antenna also changes the polarization. The medium in which the wave travels can in certain cases after polarization of the wave as it appears in the aperture could be different. So this is I'm giving you an example. This is in a if you may not have any sophisticated equipment, have a rotating dipole, make a rotating dipole or a horn radiation pattern, and from this you can get that ellipse. See, except the sense of the polarization, which you should have a right hand or left hand helix, you can get all the parameters, all the study of the polarization of an antenna with this rotating dipole thing. Now, what are the polarization losses? You see, in general, two or linearly polarized antennas that are rotated for each other by an angle phi, the power loss due to the polarization mismatch will be described by this factor cos square phi. So it could be maximum 1 or it could be 0. Hence, if both the antennas have the same polarization, the angle between them radiated E field is 0, and so power loss is 0. There is no power loss due to depolarization mismatch. Otherwise, you can find out whatsoever is the angle and you can find out the polarization loss. A side note, this explains why moving the cell phone or your head to a different angles can sometimes increase reception. Cell phones antennas are often linearly polarized, so rotating the phone. Now, I don't want to go further, but let me tell you one thing. This suppose if you are in a big city where both the sides are big tall building, and the tower or transmitter is in one corner of the side in the street, and you are on the perpendicular side. Okay, still you get the signal. You know why? Because although they travel through the straight line, but there is also a creeping wave. Whether it's even creeping waves exist at higher frequencies, lower frequencies, and that the diffraction takes place. If there is a range there, you get a better signal. It is like this only in one corner. If you have got a bright lamp, a street lamp, all the buildings are there, but you get the light on the perpendicular to it, even quite far away. So the same phenomena is applicable here, and I think a researcher can do a wonderful thing. They can make a model of a city for mobile communications. I'm just skipping it. These are the various types of slots where you can get it. Here you get the zero signal, here you get the maximum signal. Those things have been shown. I already explained it. So if the antenna is polarized match, then polarization loss factor is 1. If they are polarization mismatch, they are orthogonal, there is polarization loss factor is 0. So polarization loss factor varies between 0 to 1. So now, the polarization of a reciprocal antenna is defined by the polarization of the wave radiated by the antenna, and measurement of the polarization of the antenna requires determination of the polarization of this wave. On the receiving side, contrary of this is applicable. So, following are some of the methods: measurement of the ratio of the amplitude of two orthogonal linear polarizations, measurement of the ratio of the amplitude of two orthogonal polarizations is given in any book. Measurement of the ratio of the amplitude of two orthogonal polarizations in the phases, you can find out your antenna polarization characteristics. But best is what I told you, the rotating dipole. This is a typical polarization pattern in a polar solenoid of rotating dipole. Okay, so it is a linear voltage scale. This is decibel pulse scale. A beautiful dipole we made it. And if you do antenna pattern for circularly polarized peak, you see it here. You get almost a single polarization, means there is nothing. When you go here, you get the electrical polarization. So I'm going to talk a little bit of, I've got another 10 minutes to talk on antennas, then noise. See, noise is another important factor. The earlier speaker has not talked anything about noise. He has only talked that he has been transmitting, whether he is receiving or not, because for receiver, the noise factor is very high. Why we are not using dielectric antennas very extensively, in spite of their small size, because they are lossy and it increases the antenna. I mean, the noise figure, it increases of the antenna system. So what is noise? Noise is unwanted input signal, since there is always a random motion or movement of the free electrons in a conductor due to present a small amount of random current on noise. This is called noise. If a signal current in a conductor is smaller than the signal is marked by the wire, by the noise, and no amount of amplification will separate them. In addition, the noise generated by the circuit will add to the noise current already present, and the SNR at the output of the amplifier will be smaller than at the input. See, why we want to make antennas less lossy and why noise is becoming important, because if the antenna has got the loss, those things directly gets to the system noise figure, that G by T. So antenna to the extent should be less lossy. So that get directly added to this one. Now you see here, I'm saying the noise voltage across the open end of a conductor is this is a very important formula. If you slightly solve it, it becomes a noise spectral density, power spectral density H F by kT to power HF kT minus 1. Never mind. Now, here I'm not going to go further. They got all known things. I have not put anything else. K is the Boltzmann's constant. So I want to talk to the researchers. The Boltzmann's constant, how does it come? Suddenly it appears. I would request them to go to their 12th or BSc classes. So Boltzmann's constant is the proportionality factor that results from kinetic energy of a particle. And this noise is coming because of the kinetic energy, not the potential energy. So you have to correlate your physics to this factor. Okay, and kinetic energy of a particle in a gas with the thermodynamic temperature of the gas. It occurs with Planck's law of black body radiation, Boltzmann's entropy formula, and it has dimensions of energy divided by the temperature, and that's why this KT becomes very important. I think you should derive it and check it. Now, why I put this formula is that we say the noise temperature, on cooling, the noise temperature will be less. Okay, or noise figure will be less. But do you see that if I put T is equal to 0 Kelvin, then what it becomes? And what this total factor becomes? 0. The physical significance of that one is that you cannot go on cooling antenna or amplifier or any of your electron devices. You can go up to certain extent, but you cannot go to absolute 0, because absolute 0, the random motion of the electrons is stopped. So there is no question of measuring the resistance, there is no question of measuring anything, because current itself will not pass. Current also is for electron. So we can never go to T. If typical question is asked, can I go on cooling my amplifier, oscillator, or a antenna to 0 Kelvin? What will happen? Nothing will happen. Nothing we will get it. So antenna temperature is a parameter that describes how much noise an antenna produces or picks up in the given environment. The temperature is not the physical temperature of the antenna. Moreover, an antenna does not have an intrinsic antenna temperature except the copper losses associated with it. Rather, the temperature depends on its gain pattern, thermal environment, and that is placed in it. Antenna temperature is given by this. So see, here you see, I put it I think by see, I put it here. You can check it. Or go back. See, you can see R theta phi. This is the radiation pattern of an antenna, and T theta phi is the temperature coming from various sources. Could it be sun? Could it be earth, moon? Even a lossy environment nearby can also be there. If you got an atmosphere, lossy atmosphere, that has got a dual effect. It attenuates your signal, at the same time that particular attenuation generates the noise. Okay, and that noise has to be added into the noise figure. So totally you see the system is TA plus TR, and TA is equal to TM plus TS plus TF. So this is the total antenna temperature, where TM is noise measurement contribution from the main reflector. Reflection is equal to noise temperature from main lobe, side lobes, diffractions, cross polarization, noise due to sub-reflector, etc. And if your back lobe looks at the earth, the albedo temperature is 230 Kelvin. So you have to integrate your back lobe or side lobe to that extent and add it to the TA. And that's why this formula is given. A parameter often encountered is specification sheet for antennas that operates in certain environments in the radio of gain antenna divided by the antenna temperature or system noise term. If a receiver is specified, the parameter is written as G by T. That's also called figure of merit. Now, this is a terrestrial window. I just want to tell you. You see here, if you say it's 2.76 or 2.53 or 2.57, many researchers take this is the cosmic background noise because of the Big Bang phenomena. If you go into lower frequency below 1 gigahertz, it's the non-thermal background which increases. So an antenna, say suppose you are operating 100 gigahertz, 100 megahertz or 200 megahertz, you have to take minimum 1000 to 1400 Kelvin as a background noise. If you are going into the higher optical band, then you have to take a quantum limit which takes over the thermal noise. This is the only band from 1 gigahertz to almost 20 gigahertz. You have the minimum noise, background noise. Max, you don't have to add this one. You have to add only the noise from the albedo, sun, etc. If you see the sun, you can get 10,000 to 15,000 Kelvin, that sort of thing. And here are the water bands, as absorption S2, O2, etc. If you are operating in these things, as I told you, not only it attenuates the signal, it also it puts the noise into system. H and OS lines are hydroxyl lines, and they are almost in the L band, and they are used for finding out the extraterrestrial intelligence or life in if anywhere place, because this is called water hole. If hydroxyl ions exist, it means there is a water in that place. So sources of noise are 270 to 300 Kelvin. Atmospheric losses depends on the weather and frequency. Suppose you have got a 3 dB atmospheric loss, it attenuates your signal by 3 dB, and the KTB becomes 2 minus 1 into 300. So almost 300 Kelvin. Again, you have to add to your noise plane. So Luni temperature is typically 250 Kelvin. Luni means moon. Sun temperature could vary from 10,000 to 30,000 Kelvin. And we never allow the antennas to look at the sun. Sometimes our ground station antennas, because of the geometry, looks into the sun. Sometimes, and we call sun outage. So that's only for minimum time. At that time, another antenna has to be put. Copper losses, side lobe absorption, these are the things. The mounting platform structures causes loss of signals due to the blockage, multipath interference. Also, sometimes they give they also got, so highly directional antennas, you got side lobe, etc. there. So they do coupling from there. Those things also have to be taken into account. Quantities for interest includes pattern, distortion, antennas to antenna spatial coupling, radiation hazard pattern. So an antenna engineer life is not so simple. You suppose you make a small array of your antenna, even with dielectric resonators, you have to see the coupling and radiation hazard calculations. Say the mutual coupling, the coupling between the two antennas, coupling from the environments are very important for a beautiful and good antenna design. Information needed both in far and near fields. The antenna for aerospace applications should be, temperature should be minus 100 to sometimes we go to 150 degree. Requisite power handling capability in ultra vacuum, designed to withstand the radiation environment, launch of vibrations, body effects of the aerospace platform, because aerospace platform, be it's a aircraft, fighter, satellite, launch vehicles, they are the antenna platform. So each antenna has got its own coupling on the other antenna, irrespective of the different frequency of operation, because no antenna has got a zero, what you call voltage or current at a even far away frequency. There is certain amount of current and voltage there, so certain amount of coupling also will be there. The antenna for special applications, environment effects on back and electronics devices should be there. We should take maximum care of grounding it, because otherwise back there is a charge gets built up, and if you don't ground it, you may not get sometimes the propagation. When the satellite enters, into the space, like our space recovery equipment, uh, experiment which we did, or when Gaganyaan will enter or the missiles enter, then the outside temperature becomes almost 4,000 to 5,000 Kelvin, and nothing can propagate through it except they say some person say ELF. So those things we have to take care that does not affect the back end electronic. So effect of acute orbit control for pointing. So if you are going to Ka band and V band antenna, etc., you have to send a beacon, and beacon has to be tracked with monopulse tracking and send a signal, and that controls the acute orbit control. So frequency isolation, polarization discrimination are most important, and meet the EM radio isolations. So these are omnidirectional antenna. There's nothing is like omnidirectional antenna. It should operate in a hypothetical omnidirectional antenna is matches with the Poincare sphere. It radiates in all directions, and the parallel nearest practical antenna, omnidirectional antenna, is a in turnstile antenna. Okay, and we can call it. We usually call it more near to isotropic, because theoretical isotropic antenna is this one. And omnidirectional antenna, misnomer is there. We can have a radiation pattern, same radiation pattern in one plane. Then also it's omnidirectional pattern, horizontal plane, vertical plane, 45-degree, etc. Then we can say. So some important definitions which are essential for antenna for space applications, but not generally cared for other antenna, is isotropic antenna. That, and what is the gain for that with respect to isotropic? Isotropicity is the positive number of magnitude less than or equal to unity, and when you completely integrate the whole power, divide by whole radiation power, measured radiation power in a 4 pi stadium, divide by 4 pi, then you get the thing, and this you can also get the efficiency for that one. So we use for omni antennas actively for UHF, L, S, and C equipment. Achieving omnidirectional antennas or omni coverage is as complex as designing a highly narrow beam antennas. And coverage requirements for the satellite or rocket, we have got almost 85% better than radiation sphere of a gain of minus 10 dB. As I said, we can never have a isotropic antenna or omnidirectional antenna in all directions. Polarization RFC, LFC, we use it. Two antenna concept we use to fill the nulls. This is a omnidirectional antenna characteristic for a inset, how we measured it. Now I'll just going to give an example. Dichroic mirror is a frequency selective surface enabling simultaneous operation at multiple frequency bands. This we designed 32-meter deep space network antenna, which is available near Bangalore. At S and X band, multiple focal points can be generated, placing the field system for frequency recognition. Dichroic mirror designed for DSN allows X-band signals to pass through with a negligible loss at the same time acting reflector for S-band. And if you take a clue from the earlier speaker, maybe you can design some antenna system by putting a glass or something else and print the grids on that one. Now, our mirror is 40 thick. It's a perforated plate filled with Teflon plugs designed to have dual pass. It was done by Godrej with our design. This is the antenna. So here is the feed. From the reflected comes out. This is a waveguide. Here is one plane reflector, and here is a X-band horn, which from here it gets reflected. And here this dichroic mirror allows the S-band to go. So, but S-band and allows the X-band to go, but S-band gets reflected. We get it. Then here we are proposing to put a 200 gigahertz thing. So another reflector. So this total thing can go up to 200. This is the dichroic mirror action S-band. This is the HOR. This is the waveguide. One can pass through the wave when one can even walk through the waveguide. This man is standing, you can walk through it. I have walked in the waveguide. This was made everything in India. Nothing we have imported. It was designed by my group at ISRO Satellite Center when I was the associate director and the group director. And it was fabricated by ECIL, assembled by STRAC. This ray tracing we used. It's simple ray tracing. This is the simulated release X band. You see how beautiful we have got the side lobe in this one. This is the 32-meter antenna. This tracks Chandrayaan, Mangalyaan, and also provides support to NASA and ESA. So thank you very much. I've got. Do I have another 2 minutes, Dr. Taimur?
Yes, sir. 2 minutes. Yes, no problem. You can take.
I want to tell the researchers, but you don't need a very sophisticated facility to do research, okay, in your institute, because sometimes the finance is a problem in academic institutes, and whatsoever is available, the director has got a headache because I had been vice chancellor. He has to distribute among all the departments. So see how we did the evolution of antennas. This is the Aryabhatta antenna. We did not have a non-metallic structure. So this I'm talking about the 73. We had a TA table, put a wooden table and GR admittance bridge. This is Aryabhatta flight model. And we had a telescopic fiberglass mask which was given by Dr. Kalam when he was head of FRBD, my good friend as well as senior and mentor. So this was the we used to change the characteristic and put a here winching mechanism. What you see is a simple GR admittance bridge which none of you must have seen except Professor Day. This is the Apple spacecraft. We put the absorbers here and put absorbers here. We had a scale model, tested it, and mind it, this was an electricity board tower which I bought it for 10,000 rupees at the time, and it was an open field in Pina Industrial Estate. Now all are, and we had no electromagnetic. And this is an impedance measurement of Apple spacecraft. We cut off the ground segment. We had a non-metallic structure. We put wheels on that one. Cut off those things also by putting a beautiful absorbers. Did the measurements, and all these things are away, means almost hundreds of meters away. So we had a beautiful open space, EM-free thing, and we put then Professor U.R. Rao, who was the director at that time, put the bull here, and this photograph was put into some American and European magazine. They say India has got a means of fabricating satellites, but no means of transporting them. Mind it, Apple was a first communication satellite which has a C-band and cable. This then we made an open enclosed chamber, putting absorbers. Here IRS was tested. Now that field is also not existing. Then we made a RF shielded enclosed chamber ourselves. See, Dr. Sugandhi of Christ University has made it. So you can also make a beautiful enclosed chamber, not costing more than few lakhs. Now we have got the best compact antenna test facility where we test the whole satellite for its up and down links. This is, you can see, in set 2B is being tested for all frequencies. So we started in 1973. This is an antenna which was tracking the Aryabhat manually, and you see there was a telemetry array, and this was a 148 telecommand array. What you see, a black triangle, was a bamboo we painted black because at that time fiberglass was not available in the country. Then we developed a 32 meter, 10 meter, 11 meter antennas. Here we used the dielectric, which costed some 10 to 20,000 rupees against that 2,000, 2 lakhs or $200,000 imported one with the multi-mode horn, etc. But we realized the same thing we did with the electric, Garware dielectric, how the Garware Teflon. This is the 32 meter. So our progress started from this one to 70% efficiency to almost 65 to 70% efficiency for a deep space network. So I feel India is an aspiring country. If I could inspire some researchers, I'll be very happy to it. And this was prepared in the last moment because I was not well for last 10 days. I was taken suddenly ill. So you see, we could launch a satellite, rocket, We also have got a toddler who is interested in laptop. So India is definitely an aspiring country. I don't consider India a developing country. I consider India a developed country. We are developed in defense. We are developed in aerospace. We are developed in space. We are developed in atomic energy. Also in certain fields of medical. And I am told as a vice chancellor that our students are not employable. Yeah, maybe all students, because the fault lies with the academicians, but majority of our students are quite good in ISRO, DRDO, and CSIR. Uh, I mean, in my long association of almost a half a century, the students trained from abroad and from IITs were less than 50 in 18,000 of ISRO. All were other colleges. So please don't get disappointed. You can do wonders. We have done wonders. Thank you very much, Dr. Taimur and other listeners.
Thank you, sir. Thank you very much for opening so many research windows before all of us. Definitely, we will pick up some of them in near future. Now, there are some queries from participant side, sir.
Sure,
Like
go ahead.
first one, different methods for obtaining circular polarization in the practical antenna, not what we have seen in books, basically, because your talk was started by considering the things that what we have studied in the book, that is entirely different what we really implement.
Okay. I mean, now it's, I'll tell you all the examples. If you take the microstrip antenna, you have to feed, you can feed it through the diagonally, or you can put two 90-degree probes, when, one plane, one side, another side, and you can get circular polarization. If you are going for a waveguides, horns, you can use the pin polarizers. You can use even a simple Teflon plate. You can insert it, design it. That also will give you good polarization. And such polarizations, there, I mean, what you call polarization losses are very less, and your electricity is wonderfully well. So you can design those things. And if you want a very highly accurate polarization mesh thing like RSC or LSC, then you have to design a helix antenna. And if you are using dielectric antennas, not the dielectric resonator antennas, I'm talking about like if you use a Teflon, or if you use perspex, which is very high, or use other things, many things are available, Stiex, polypropylene, all those things, if you use it, which are less lossy, you can insert either mechanical or a polarizer inside it, or when you are launching them from a waveguide or a horn, then there itself you can launch using the polarization. Polarizations are many types, like you can have film polarization, you can have a plate polarizer, you can have the dielectric polarizers, Teflon, etc. in that one, and you can feed from the perpendicular two poles in opposite to each other. So you get the RSC one side, LSC one side, and the phase shift will be given by the polarizer plates.
Okay, thank you, sir. Thank you once again, because there are several other queries. For that one, I will directly direct the participant to you, because it is already 15 minutes late.
Or what
yes.
I said, you can collect all of them and send
Yes,
to me,
yes,
and
yes, sure.
I'll send the reply to you.
Definitely, sir. Sure, sir, sure. With this, I must say my sincere thanks to you for accepting my invitation first, and for delivering a wonderful talk on covering all the things which we not generally see in our day-to-day life. With this, I thank you once again, sir, and see you in near future also for giving such a wonderful talk.
Sure. And thanks, Dr. Taimur Khan, for inviting me.
Thank you, sir. Thank you.
Bye, and good luck to everybody.
Thank you, sir. Thank you. Okay. Is the screen visible? Is the screen visible to you?
No, sir.
No. No. Still it is not there.
I think so.
Okay. Why the screen is not? Is it visible?
Yes, sir. Now it is.
Okay. Now the third speaker for the first day of this ongoing Indo-Canada's course, Dr. Sonik Kiran Kumar Das is with us, who is alumni of National Institute of Technology, Silchar. Now, without giving much detail about that, I would just reading the biography which is available with me before inviting Dr. Das for delivering the talk. Dr. Das was born on 2nd February 1992 in Odisha, India. He received his BTech in Electronics and Communication Engineering from Centurion University, Bhubaneswar, India in 2013. In MTech in Communication System Engineering from KIIT University, Bhubaneswar, India in 2015, and PhD from National Institute of Technology, Silchar, Assam in 2018. From January 2018 to April 2019, he worked as an assistant professor in the Department of Electronics and Communication Engineering at CRIST, deemed to be University, Bangalore, India. At present, he is working as a postdoctoral fellow, research fellow at Southern University of Science and Technology, China. His current research interest includes dielectric resonator antennas, self-multiplexing antennas, RF energy harvesting, MIMO antennas, etc. He has authored or co-authored over 30 research articles in a refereed journal published by IEEE, IIT, Wiley, etc., as well as in conference proceedings of repute. He is serving as an advisory editor for Wiley Engineering Report. He is also an active reviewer of several refereed journals of international repute in IEEE as well as in non-IEEE. Dr. Das has granted several grants. That's a student grant from European Microwave Association, Belgium, a special travel grant from European Microwave Week, Netherlands, foreign travel grants from Council of Scientific and Industrial Research, Government of India, for attending various international events. Currently, his research works are partially supported by National Natural Science Foundation of China and by Science and University Key Research Project of China. He is an active member of IEEE, APS, SPS, EDC USA, URSI Belgium, and IANEG Hong Kong. With this, I invite Dr. Das for starting the talk. Just wait, I'm stopping my presentation. Then you can, yes.
Just a moment, sir. I'm sharing my screen. Just a moment. Is it visible, sir?
Yes, it is visible now.
Now it is okay?
Yeah, it is good.
Okay. Okay, very good evening, good morning, as we are from different region, time zone. So I'm Dr. Soni Kiran. I'll be giving a presentation on some fundamentals of dielectric resonator antennas and their applications in engineering. So as we already that our previous speakers have given very detailed idea about the dielectric resonator, I mean the advanced dielectric resonator antenna, and a recent speaker told about various aspects of antenna engineering. And but my topic will be just about I'll giving the fundamentals of DRA. I'll give about the fundamentals of DRA, like I'll be covering the introduction, and then I'll go for the, just a moment. Yes.
Dr. Sonik, on bottom side, one icon is there. You hide that icon.
Yes, yes, sir. I'm hiding that one. That was actually creating
okay.
some problem.
Okay, yes, now it is good.
Can you see right now?
Yes. No, now it is fine. Presentation. Just go in the slideshow mode.
Okay.
Yes. Yeah.
Okay. Sorry for the interruption. And then I'll be giving the brief idea like how the dielectric resonator antenna and why it is entering the antenna, why people started using dielectric material as antenna, then about its fundamental characteristics like the performance, the design challenges, and DRSA, all these things. Then I'll be focusing about the performance improvement techniques and the applications. However, as we see this is a long topic. I have divided this in two parts. So one part I'll be discussing today, and then the next lecture I'll be discussing the next part. So about part one, just moving to the introduction. As we understand that the present era of communication, if you see, it has been rapidly changing from lower frequency range to higher frequency range. Okay, but in that manner, if we look into the antenna aspects, all the whatever the microstrip or microwave antennas that are available, that were available prior to 1983, those antennas were not easily can be scaled for higher frequency. Okay, because they generally suffer with conduction loss and low efficiency, etc. So they can be easily they can be scaled, but there are some difficulty in scaling those antennas for higher frequency. So these two problems actually encourage the people to look into the another suitable alternative, that is DRA. And this was first proposed by Stuart A. Long of University of Houston in 1983. And it is simple antenna. If you just look into that, there is a dielectric material and which act as a resonator upon excitation, and that also radiates when we excite certain resonating modes. So simply we can say it's a dielectric resonator antenna. Sometimes also people say it's a DR antenna, and sometimes also people say it's a radio antenna which uses a dielectric material. The construction is also very simple. We need to use the shellac material, which we need to put on a metallic surface. That is known as the ground plane, and we need to excite proper excitation mode so that it can radiate. Just have an idea about how this antenna started here. But if you just move to back of 1939, the first the other Richmond he introduced known as this paper, that is dielectric resonators. There he didn't talk about the antenna part, but he just discussed about the dielectric resonators and its for different applications. But he didn't mention about exactly for antenna. But if you just look into that, then the next 1983, Stuart A. Long reported this right-hand side, that paper we can see, the resonant cylindrical dielectric cavity antenna. This was proposed by Stuart A. Long and his team in 1983. Actually, these two papers are very much important if someone is going for antenna and dielectric resonator antenna research. He should go into these two papers at least, because this gives the basic idea about the dielectric resonator antenna. So this is just a brief history how the research started. In 1939, Richmond, that I discussed in the last slide, he introduced the DR as a high quality factor, which is a non-metallic resonator, okay, and that is applicable for filter and oscillator purpose. But he didn't discuss about the antenna part. Then 20 years later, in between the 20 years, there is no such report. There is no such significant report on dielectric resonator for the next 20 years. But in 1960, the researchers led by Oke and Barras, he just investigated DRA with some crystal like TiO2 material. He discussed the different characteristics of dielectric resonator only. In that manner, again in 1960, in the same year, mid of 1960, there was extensive theoretical study and experimental examination was available on DRA. On DRA, actually, this is not DRA. Then mid of 1975, there was a detailed theory that explains the different modes of dielectric resonator. But those modes were not radiating modes. Okay, that was done by Bladel, and he has done some works on mainly for DRA modes. He discussed about the detailed DRA modes, what are the resonant modes, all these things. Then in 1983, we found the first work that was reported DR as an antenna. They used a low Q factor. If you just look in the left side, 1939, the Rismore introduced high Q factor DR. But in 1983, Stuart and Long introduced the low Q factor DR. Means which is once the Q factor is low and it is placed on a metallic ground plane and giving the proper excitation, which starts radiating the electromagnetic waves into the space. Okay, so that is how the history of antenna, the history of dielectric resonator as an antenna. Okay, this is how the dielectric resonator moved from as a resonator to an antenna. But why we are using all these dielectric resonator antenna? What are the advantages? It has mainly two advantages. Like one is flexibility in modeling and design. Another one is advanced performance characteristics. What are the flexibility? If we just look into the DRA, there are mainly three fundamental, not exactly fundamental, three primary shape of DRA is available. One is hemisphere. In the bottom, you can see in the hemisphere generally there is one controlling parameter, that is R. So we consider the degree of freedom is 0. Okay, and because then the next one that comes cylinder. Cylinder, we can see there is one radius. It has the radius and the height. Okay, and the characteristic of that cylinder or the performance of that cylindrical DR depends upon the ratio of radius to height. Okay, so it has the degree of freedom 1. It has two parameters. As we are taking the ratio, we consider it as the degree of freedom is 1. The next that comes rectangular dielectric resonator. In rectangular dielectric resonator, we can see it has a length, width as well as height. So length to height ratio and width to height ratio, that also matters, and that controls the performance. So as we find here, there are two ratios. So we consider there are 2 degree of freedoms for rectangular DRA. So if you compare these three shape of dielectric resonator, we can say that rectangular DRA gives a much better flexibility than the other dielectric resonators. Okay. So apart from its size, we can also find some other freedom in terms of permittivity. Even we keep the for cylindrical DRA, if we keep the radius and height same, I mean constant, and we keep on changing the permittivity of that dielectric resonator, then its performance also changes. And it supports multiple feeding mechanisms that we'll look into the next slides. What are the different feeding mechanisms? And in terms of advanced performance, we can say it generally gives better bandwidth, and conduction length is very less, and it supports several radiating modes, high efficiency, and maintenance free. Okay, as it is susceptible to high temperature. Then what are the performance features? The performance features, like the dielectric resonator antenna, it can operate, it can deliver a very narrow band, as well as it can give a wide band of around 20%, or we can give a ultra wide band also. But that depends upon the permittivity or epsilon, relative permittivity, or we can say epsilon R. And epsilon R, if we are just taking for few percentage of few with higher, if you'll take the epsilon R higher value, then we'll get the narrow bandwidth, and if you decrease the relative permittivity value, we'll get wider bandwidth. That is a very basic thing. And different far field radiation pattern also it supports, and tolerance error it has less tolerance error as compared to microstrip antennas at higher frequency, mainly not at lower frequency. But if you just compare this antenna with the microstrip antenna at higher frequency, it has some better advantage. It has a high dielectric strength and hence higher power handling capability. So this is also some advantages for which people started using. So even if it gives some advantages, still it has a lot of challenges. Challenges means which are possible we can make over those challenges. Like if it keeps on epsilon r, that the dr size keeps on decreasing. I mean the performance, in terms of performance, if we for the same performance, if it keeps on the epsilon r increasing, the dr size can be decreased. But what happens if it keeps on continuously increasing the epsilon r, then the key factor also keeps on increasing, and as a result, as the key factor keeps on increasing, it results narrow bandwidth. Okay, so that is one challenge. So we need to, whenever we are just comparing the epsilon r, the dra size, we need to keep on eye on the performance like bandwidth also. It should not get affected. I mean, we need to find a we need to find a point where it is matching our requirement. And for other antennas, like to achieve requisite bandwidth, the antenna, if it just like GSM or PCS antenna, like the popular applications, to achieve this, the epsilon r should be less than 30. And in case we are keeping that is less than 30, below 3 gigahertz, then the antenna size becomes large. So that is also a problem. Like this is not only the problem with this antenna. We can say even if we go for other antennas, when we use something for the lower band, of course the antenna size becomes large. But however, we need to look into this concept also, how epsilon r is affecting the antenna size. And there is the image theory. As we know, image theory using that is the ground plane concept. Okay, and that reduces this antenna size. But sometimes what happens, the ground plane increases the volume of the whole antenna. Okay, as I told that this antenna is mainly based upon a ground plane, that I will figure out in the next slide also what are the different parts, how the ground plane is exactly affecting, how the thickness and how the material of this is affecting the performance. That I will look into next, that I will discuss in the next slide. Then the research on DRA is based on handheld antennas is not up to the mark, because as we see, because DRA is a 3D material. Okay, when it becomes a 3D material for the handheld device, sometimes it becomes application restraint. Okay, because microstrip patch antenna generally it's just like a layer. Okay, it doesn't bother about. I mean, the size of the antenna is not going to be affected much. I mean, size of the device is not going to be affected much. But in case of DRA, as we can see it as a physical, I mean, the height is some millimeter. Okay, so sometimes it may be a problem for the handheld or compact device. And ensuring circular polarization with a simple approach, it's I mean, we need to do a lot of things for circular polarization in dielectric regenerator antennas, and that becomes sometimes, because from fabrication point of view, that becomes difficult, not impossible, but because it's quite tricky. Then ensuring high gain more than average 5 degrees simple technique is still missing. Okay, I hope you understand what I mean to say. Like the general antenna, the dielectric regenerator antenna gives an average gain of 5 dBi. Okay, but without much I mean complex techniques, with a simple technique, higher gain is still missing till now. And fabrication and tailoring is a big challenge for some, because those people who have been working on DRA, they knows that in comparison to microstrip patch antenna, the fabrication of DRA is quite it's a challenge. For sometimes it is restrained. And the development of DRA on silicon-based IC surface in form of MIC, that also need to be a lot of that needs a lot of investigation. That is not yet up to mark. So just look into the what are the different DRA shapes. As in the previous slide, I have told that hemispherical, cylindrical, and rectangular, they are the very basic shape. And apart from this, we can see it can be a conical shape, it can be triangular, and this triangular also it can be equilateral or something, and a hexagonal shape. On the right hand side, we can see people have also used some advanced shape, or we can say super shape DRA. We can see they have used a dumbbell shape on the right hand side. Some people have used A shape, like English alphabet A shape, and here it is a pawn shaped DRA. This one is the, let me highlight here. We can see, so we can see it is a pawn shaped, and here it is a splitted DRA, that hemispherically splitted into two parts. And it is also, we can see a hybrid shape. They have used step shape, and it is hexagonal shape, because all these new advanced shapes are people mainly used to achieve either lightweight or for wider bandwidth. There are some regions. Okay, and then what are the different parts? Those people who are just new to the DRA, they should have an idea about what are the basic things that are required for the dielectric resonator antenna. The first basic thing that we know is ground plane. Okay, ground plane means, as we know, as we know that ground plane is nothing but it must be a conducting plane. Okay, above which the DRA should be mounted. We can see in the right hand side figure. Orange color one is the ground plane, above which the resonator, that is the dielectric resonator. Brown color, that is placed. Okay, it may be a three-dimensional copper, steel plate, or a conductive coated dielectric switch. Okay, so if you'll see that people who are in the literature, that there are different kind of ground planes people have been used. Some people use that, of course, depend upon the application. Sometimes we use the three-dimensional, I mean thick, of some millimeter, like 1 millimeter, 2 millimeter thickness ground plane. Sometimes also we used to take some dielectric sheet, and above that there should be a coating like FR4 with some coating, FR4 substrate with some conducting coating. That also can be used for ground plane. However, there is we need to there is separate purpose. When the conductive coating sheet, I mean, whenever you are using the conductive coating sheet like FR4 with some conductive coating, or we are getting taking articulated sheet with conductive coating, those are mainly used for medium or multi-band operation. Okay, medium band, narrow band, or multi-band operation. In case of the user wants the antenna to design for ultra wide band or wide band purpose, then that should be conducting plane, and that should be a thicker one. Okay, so this is a basic thing that we should keep in mind, that if we are designing the antenna for wider band, we need to use a conducting plane instead of a conducting sheet. Okay, and in case we are designing our antenna for a narrow band or multi-band, we can use a conducting sheet like with FR4 with conducting sheet, and or articulated or something like articulated with conducting sheet. Okay, and apart from ground plane, the next one that is required, that is a dielectric resonator. That is nothing but the topic of my presentation of this course only. It is mainly used for resonating, as well as for it resonates, then it starts radiating. This part is placed upon the ground plane depending upon the aspect ratio and the Q factor. Okay, aspect ratio and Q factor, the resonant frequency is totally calculated. Means the radius, height, and the Q factor, as well as the epsilon r. All these things controls the frequency of, I mean, the resonating frequency of this dielectric resonator. Then the third part that comes, that is nothing but the feed. The type of port used, the feed, as we can see, I have shown a sample feed only, but there are multiple feeding technology that I will discuss in the next slides. Okay, and depending upon the type of feed we are using, sometimes we are using the probe feed, sometimes microstrip line coupling, sometimes aperture coupling. So this kind of techniques, as well as the placement of the position of the feed. The feed position also controls the performance of the antenna. Like sometimes we use different, like for wideband we need to use this kind of feeding. For narrowband we can use this kind of feeding. So there are different that depends upon the feeding location. So as we can summarize from this slide that the feed and the resonator, these are the feed and the resonator shape, they mostly controls the performance of the antenna, or we can see the frequency of the antenna. Yes, so this is a quite interesting part actually. As I told, that one advantage of dielectric resonator antenna is it supports a wide variety of feeding mechanism. Okay, so first one that comes, the very basic one, that is the aperture coupling. Aperture coupling is nothing but when we some power is coupled inside the DRA through the aperture slot. Aperture is nothing but, we can say, it's a kind of slot that is made on the ground plane over which the DRA should be mounted. And small rectangular slot and annular slot, as we can see here, these are mainly used for that mainly used aperture. They are mainly the very common apertures actually, but sometimes we need to use the cross-shaped slot and C-shaped. We can see the cross-shaped and the C-shaped slot. These are mainly used for circular polarization. Okay, so we should have some basic idea before entering the DRA. Like if we are just using only slot, I mean the rectangular slot, and we started checking that actually, so that it doesn't mean anything, because these are some if we just look into the literature, so these are the very basic techniques that are used for circular polarization. We can use the cross slot technique or the C-type slot technique, that easily we can have the circular polarization. This approach uses microstrip line and avoids on-and-paired coupling and counterfeit radiation direction from the field line. Means this basically it tells that by using this technique we can have a better matching and unwanted coupling. We can avoid the unwanted couplings. The next one that comes probe coupling. Probe coupling means when we are using a, as we know the field, generally we are using the SMA probe, SMA connector. So this is nothing but we can say this is a SMA connector, like it looks like, just we assume that this is a SMA connector, and here also, and we can see that the probe can be used at different places. Sometimes we can use to just the coaxial transmission line as shown above. The probe is a coaxial transmission line that extends from the bottom of the ground plane. The probe can be placed at the center of the DRA. As in the middle figure, we can see the probe is just placed at the center of the DRA. Okay, and sometimes we can place it which is just adjacent to the DRA wall, that is on the left side. Okay. Sometimes it is directly coupled to the DRA wall, and sometimes via through metal strip that is given. The figure is given on the right hand side. We can see that they are the feeding mechanism. Though we have used the probe feeding, but directly we are not giving the feed to DRA. We are using a conducting sheet that is just pasted on the side wall of the DRA. Okay, and there should be a proper soldering between the probe and the patch, so that the rectangular patch, so that the antenna can be excited properly. So these are the different techniques and how we can use the probe for the feeding mechanism. And here actually we just need to keep two things in mind how the antenna performance gets controlled. The length of the probe, in case we are just using only probe coupling, then the length of the probe that controls the performance. In case we are going for the right hand side technique, we can see we need to use a rectangular patch. In that case, the length and width of the patch also controls the performance of the antenna. So these things can be taken into consideration for tuning the frequency. Then the next one that comes microstrip line coupling. And microstrip line coupling is the very common coupling, because we have seen many circuits in electronic circuits. If you just open up any PCB board, we can see that this kind of coupling, but we rarely see this kind of coupling technique with DRA. Okay, so this as we know that this kind of coupling we can use in DRA, because this will be very much helpful for microwave circuits. Okay, and it also helps for exploring the fundamental modes like HEM11 in cylindrical shape DRA and TJL11 in rectangular shape DRA. So this is also one kind of coupling technique. As we just keep in mind, when you just compare this dielectric resonator antenna with the other antennas like very popular microstrip line antennas, okay, microstrip patch antennas. So we can see there is a lot of variety of feeding mechanism we can use here. Okay, and by using a lot of feeding mechanism, we can improve the performance, like or we can have some other performance like circular polarization. All these things we can ensure in the same antenna. The fourth one that comes, that is coplanar coupling. I mean that we know that CPW, we commonly tell it is CPW feeding. Okay, so this kind of feeding also can be used, but as we have figured out here, that just look it. I think the figure is just double here in the middle. It is just repeated, no problem. So we can see here three types of feeding. Okay, as of open circuit microstrip line, open circuit coplanar waveguide. Okay, we can also use the coupling technique for dielectric resonators as shown above. And sometimes here we can say we have just used only the one feeding. This is a very basic CPW technique. Okay, and this technique sometimes we can extend this stop. Okay, not extend stop exactly, I mean the stop in the slot. Okay, and sometimes we can change this one to this kind of additional stop, okay, or sometimes we can use the loop, additional loop, and that can be incorporated for controlling the impedance matching. Okay, this kind of things. Then generally this stop and this loop kind of things is mainly used for impedance matching. Okay, it may be noted that among others, the coplanar loop offers non-obstructing coupling, and here in all the cases, generally large coplanar feed guarantees proper coupling, while small coplanar feed avoids unnecessary backloop radiation. Each has some plus and minus, and that depends upon our application, or we can say our requirement. So which kind of coupling we can use. Even just by looking into this figure, we can say that even in coplanar coupling also we have three options: what kind of coupling we need to use, and or what we can use as per our requirement. The fifth one that comes dialectic image guide coupling. So this is very interesting, and even in the literature also we find very rare paper on this kind of coupling. Okay, dialectic image guide coupling seems to be more advanced than the microstrip line for millimeter wave range, for millimeter wave communication. Okay, it mainly minimizes the last conductor loss and affords improved couplings by operating the guide closer to the cutoff frequency as shown above. Okay, so as they have told that this kind of technique can be used for millimeter wave technique. Okay, we can also use this technique for feeding a series of antennas, series of DRA, or we can say array of DRAs. This technique can also be used. Okay, so let's move to the next part, that we already discussed what are the basic things of DRA, what is the feeding techniques, what are the different parts of DRA, what are the advantages. Now let's move into the performance improvement techniques. Okay, so even if you know all these techniques, all these fundamental features, we need to have some idea about the basic idea about how we can improve the performance. Performance means if you just look into the DRA, all the performance we can divide, segregated into four parts. One comes in terms of bandwidth, the next one may be in gain, or someone may wish to ensure circular polarization, or sometimes if you are using MIMO antenna or multiple antenna or something like multiplexing antenna, we need to look into the coupling parts. Okay, I mean the mutual coupling. So this thing improving the sometimes if we are just going for array, then mutual coupling may be helpful, or if you're going for MIMO, then mutual coupling should be reduced. All these things we need to look into from a dielectric regenerative antenna perspective. So here I would like to highlight these two works that recently last year we have published these two works that completely highlights that about the performance improvement of dielectric regenerator antenna. Though it was a very long work, so we divided this work into two parts. So it was in one, on the left side article, as we can see the performance improvement. Mainly in this work, actually we have mainly highlighted the works that is related for the gain improvement, mutual coupling, and the circular polarization part. And the right hand side paper, we have mainly highlighted different techniques that has been used by researchers for bandwidth improvements. Okay, so those who are interested, just they can look into these two papers, and we have a some idea in a very, just in 10 to 12 pages we can have a lot of idea about the performance, different techniques that can be used for performance improvement. So let's discuss about those techniques. Like the first one that comes for the first technique, that is for dielectric regenerator antenna bandwidth improvement. Okay, as we know, dielectric regenerator antenna is a 3D object. Okay, by controlling its 3D parameters like the sometimes length, sometimes length width, sometimes length to height, or sometimes radius, or radius to height. By using all these things, we can easily control the bandwidth. Okay, so there are very much there are different techniques. The first techniques, the basic technique that comes stacking. Okay, these works were reported in the very early of 90s. These works were reported early of 90s. So it means placement of one dielectric resonator upon another DR. On the right hand side figure, we can see DR2 is placed upon DR1. Okay, you just as we can see, the red one is nothing but here the feeding concept. Okay, this is the probe coupling. Okay, so the placement of one DR upon another DR is nothing but stacking. What happens in this case? How this case exactly helps for the bandwidth enhancement? Because what happens, DR1, it must have a permittivity of, let's say, epsilon R1. and DR2 have a permittivity of epsilon R2. I mean, both the DRAs have different permittivity, relative permittivities. Okay, and two DRAs have two resonant frequencies because they have the different permittivity. Okay, and when they are stacked, dual resonance concept works out for broadening the antenna bandwidth. Because what happens when we are just putting the I mean this configuration, when we are just putting this configuration in simulation, what we'll find, the DR1, let's say DR1 having the permittivity of 10 and it resonates at 5 gigahertz, and DR2 having the relative permittivity of 12 and that resonates around 4 gigahertz. Okay, and when we are just placement, when they are just placed in the stacking manner, what happens? Those DRAs, we are using a single field and they resonates at two different frequencies. This technique generally helps in helps in broadening the wide bandwidth, because those DRAs, those resonance frequency lies very close to each other, as well as we get a wider bandwidth. Okay, that is a very basic technique. And sometimes also this technique can be extended by stacking of more number of DRAs. Like here we can put DR1, DR2, DR3, 4, 5, 6. We can go on. Okay, though we are not sure exactly how much up to what range that will work, but we can check in the simulation, and that has been proved from researchers that by multiple stacking also, not only dual stacking, by multiple stacking also we can enhance the bandwidth. Because in that case, when we will go for the triple stacking, what will happen? So DR1 will operate, let's say, at 4 gigahertz, DR2 will be at 4.2, then DR3 will be operating at 4.4. Okay, and as they resonate at their resonance frequency very close to each other, they will started, the bandwidth will started broadening. Okay, so that is the technique. The next technique also, some people have also introduced by introducing AR, or we can say by AR intrusion. Okay, by putting a gap in between two DRs also, it will extend the bandwidth. That there also the similar concept works out. Okay, there also the similar concept works, because the air gap is nothing but the air is also dielectric part. Okay, so I mean let's say here the antenna will be, it may have the permittivity of, let's say, 5 or 2.1, like Teflon. If you are taking Teflon, it may be 2.1, and here the antenna may, this may be some different permittivity, and air, the permittivity has the 1. Okay, so we can say it is nothing but a triple stacking. Okay, but people used to say it as the air intrusion. So this is the basic technique for in stacking, how we can enhance the bandwidth. The next technique that comes for parasitic coupling. In parasitic coupling, before going into that topic, we should have what is exactly parasitic. Parasitic is nothing but there will be one principal element, okay, and there will be some parasitic elements. Here we can see in this figure, the central DR, this DR is nothing but the principal DR, okay, and these two DRs are nothing but the parasitic DR, okay, and this dielectric resonator, this has the resonating frequency at one point, and this has the, these three will maybe have three different resonating frequencies, okay, like this may operate at 4.1, this may operate at 4.2, this one may operate at 4.3 gigahertz. Okay, and what happens, how this performance is controlled here? So what happens when we just started exciting this central one, or the principal DRA? So what will happen, these DRs also gets excited, okay, and that is known as parasitic. That's why it is known as parasitic element. Okay, because just when the other elements with different resonant frequencies are introduced in both the sides of the principal element, they can also be efficiently excited near their own resonating frequency through mutual coupling. As I told you, mutual coupling is a very important matter. Sometimes mutual coupling, that depends actually, that depends upon the mutual coupling. Sometimes people think that, not sometimes, few people think that those people who are new to antenna, like sometimes think mutual coupling is not a good term. Mutual coupling actually, it's nothing but the how the coupling happens between two elements, two nearby elements. Okay, how the performance of one element is affected by the performance of another element. Okay, and sometimes we need better good mutual. Sometimes the mutual coupling should be higher. Sometimes we expect it should be lower. Okay, that depends upon the application. But in this case, generally we expect the mutual coupling should be better. There should be more mutual coupling, so that better energy can be shared. The energies can be shared from here to here, and from the central here to here. Okay, so in this case, how the performance is generally controlled, as we know, the performance is controlled by the length and width and height of the object. Apart from that, In this case, the performance is controlled by the distance, this d. Okay, that depends upon the distance. Okay, so we cannot say that if we started keeps closing closer, and if we decrease the DRA, it may some mutual coupling we need to check actually. Okay, at what should be the value of D so that there will be proper mutual coupling. Okay, I mean the parasitic element can be excited properly by the principal DRA. Okay, so this is also a technique that can be used for parasitic coupling, because here, like as I told, this may be at operating at 4.1, 4.2, 4.2 gigahertz. This is 4.3 gigahertz, and when they all started operating at the same time instant, then we'll have a wider bandwidth. So that is the this technique also similar concept to previous one. Okay, and the next technique that comes, that is known as splitting or segmented DRA. Splitting means, or segmented is nothing but introducing air in between the DR. Okay, so that is also written here, means breaking the regular shape of the DR and inserting air gap in between. Inserting the air gap helps in between generally that affects the DRA modes. Okay, and removal of the dielectric material from where the electric field is strong, that helps, that incurs a significant increase in the resonant frequency. So what happens, we cannot blindly we cannot divide, or blindly we cannot insert air inside the DR. Okay, we need to check before moving into this step. First, in this step we need to simulate this antenna. And once we simulate, we need to check if the electric field, where it has the maximum electric field, where it has the lower electric field. Okay, and if we started removing those parts where it has the maximum electric field, okay, then what will happen, that removal of the electric material from where electric field is strong. Okay, generally in HFSS or some simulation tool, we know the, like CST also, we know the maximum electric field means where we can see the red color maximum. Okay, so if we started moving the dielectric part from those portions where it has the maximum electric field, okay, then there is a significant increase in the resonant frequency. We can check that. And once let's say here we found that it has some electric points here, higher electric fields here, then it started in the first stage, it's removed here. In the next stage also, when they simulated, they might have shown that there is an electric field in this line. Okay, so they remove this part. Okay, and once we remove that, what happens? The abrupt change in the normal electric field, because we just introduced air where the electric field was higher, and because of this abrupt change of the electric field across the discontinuous, that reduce the Q factor. Of course, once we remove some parts, okay, we can look into this in two way actually. When we take out some part from a DRA, of course the Q factor will decrease. Okay, in other way also, by looking into electric field from that point of view also, we can see where it has the highest electric field. If we started removing some part, the Q factor will start reducing, and once the Q factor starts reducing, of course that will boost to the impedance bandwidth. I mean the impedance bandwidth will increase. Always just keep one thing in mind: once the Q factor will decrease, then the bandwidth will increase. So always we need to look into that, how we can reduce the Q factor. But we cannot say that we'll just remove all the parts, all these things. That won't happen. In that case, we need to look into the electric field where it has the strength. From those parts, we need to remove the dielectric. It should be cut out where we need to insert the air. The next technique that comes, the fractal DRA. Fractal means, as we see, it's a self-similar design to maximize the effective length or increase the perimeter. Okay, or sometimes people say fractal concept is nothing but defines as it is used just to increase the electrical length with decrease in volume by the occurrence of similar pattern in a reduced manner. Just look into this figure. Okay, just look into this figure. What we did here, first we have taken a rectangular one. Then in the first iteration, we removed some part from here. Okay, so just look in the left side, second point. Fractal concept defines the increase of electrical length with decrease in volume, occurrence of similar pattern in a reduced manner. Means in the second iteration, we need to follow the same technique. We need to remove the same some part, but in a reduced manner. Means what are the tool part this tool section, I mean which section has been removed, a smaller section or smaller dimension of that tool need to be taken, and that should be put here to remove some part. Then we can find this fractal second iteration. This is just an example, just to understand. Okay, we cannot directly we cannot check all these things. For this also we need to check what is the where is the electric field strength is better. Okay, then we need to check what are the different techniques. This technique in the next slide I will speak about that. Then incorporation of this concept actually first in the DRA, it was first introduced by authors Hajishemi and Abiri, that all these references I have given in the last. I can show you. So this was I think it was introduced in DRA around 2003 or 2004 something. I'm not sure about, around 2003 or 2004. So if you look into that, what are the different kind of fractals? Because fractal we cannot say like I mean any manner we cannot go for the fractal. There is also a fractal concept is actually a very old concept. Fractal concept is very old, but introduction of fractal in DR is very not that much mature. Okay, so if you just look in the right hand side, there are different fractal techniques like Shakespeare fractal, Minosky, Apollonian gasket. All these techniques can be used. So and just to analyze the performance, we can see here, it is evident that for the rectangular geometry, the magnetic current axis almost entirely on the surface. Okay, in the left hand side, in the first figure, we can see the magnetic current is almost the entire surface. But as we increase the iteration, the surface current is confined towards the center. When we started iterating means when we started removing some part from the DRA. Okay. In the first iteration, when we started removing the parts, then the surface current confined towards the center of the DRA, thus that reduce the effective dimension of the antenna, which results in increase in the resonant frequency. Okay, so what happens here, as I told you, first we need to check what is the electric field, what is the magnetic current strength, where it is the better strength, all these things we need to check it. Then we can see when we have just started removing some part, what happens, the current strength that becomes confined at the center, and by reducing the effective dimension, okay, reducing the effective dimension of the antenna, which results in the increase in the resonant frequency. From another point of view also, we can see why the resonant frequency is increased. That is nothing but the concept of Q factor. Okay, that is just to cross check this check, but this is what the fractal concept talks about, how we need to look into the GR from fractal point of view. But in the other point of view also, we can see when we started removing some part from the DRA, the Q factor started reducing. Once the Q factor starts reducing, then of course the antenna bandwidth will increase. Okay, so always whenever you are going for the fractal concept, we can verify it from two concepts. One is from magnetic current point of view, one is from Q factor point of view. So this is all about fractal here, and this is the right hand side. There are different techniques that given. So we cannot say that all the techniques can be applicable for all the dielectric materials. That depends upon what kind of epsilon r, relative permittivity we are using, what is the frequency range, okay, and for what application we are preparing our antenna. Or we cannot say that exactly this will be used for the practical, but we must be thinking about which band or which frequency our antenna will be operating. Okay, so depending upon that, we need to look into what kind of fractal concept we can use. Okay, the next thing also, this fractal concept also that needs some mathematical calculation. Randomly we cannot look into that. Those mathematical calculation, though I have not presented here, but that we can find very easily in the any DR fractal paper, reference papers. The next concept that comes, sir, how much time I can take? Next.
10 minutes, maximum 10 minutes.
Okay, sir. Okay. Thank you. The next technique that comes, that is the hybrid or superset GR. Okay, that these figures I have almost shown in the earlier slides, but this someone might be thinking that why people are going for all these things, because we have already the splitting techniques. Sometimes we have also the fractal techniques. Why we are going for the superset DRA? So what happens? Superset DRA actually, if you just look into this, for superset DRA we cannot use any proper. Though we can when let's say here we have used a shape DRA. Okay, A-shape DRA. So generally, the main purpose of using this A-shape DRA is we cannot say that it is a part of actually, if you look into the basic of this A-shape is nothing but a rectangular, okay, and from there the authors have made it A-shape. If you look into the basic concept, it is nothing but the same concept, that is nothing but lowering the Q factor. Whenever we are removing some part, we are getting the of course we are getting the higher bandwidth, okay. But however, people used to say that it is nothing but the hybrid DR concept or superset DR concept, or sometimes those people, if someone is producing A shape, they used to say A shape, or sometimes people say to C shape, Z shape, alphabet shape. It may, that depends upon what kind of at which frequency, because always this splitting and this like the fractal concept doesn't work for all the frequency bands, okay. Like people wants to at like 8.5 gigahertz to 9 gigahertz, sometimes they don't, then the fractal concept becomes more clumsy and all these things. So people started using the super step also. But however, the main concept or the main idea of all the works is always to have a wider bandwidth with compact size and lightweight. In the right hand, the middle one, we can see here. Here also the antenna operates around from 4.2 gigahertz to 6.8, around 6.8 gigahertz, and this is nothing a dumbbell shaped DRA, okay. And the right hand side, they have used a DRA that is for, I think, UWB band, okay, that is covering starting from 2.1 to 11. That is nothing but the UWB, it's covering almost the UWB band. So these are the different techniques. Like in this technique, as I told that the patch in the right hand, this shape, the length and width of the patch, and the size and length and width of the dielectric resonator that controls the frequency or the bandwidth at which place we need to use. Then whatever I discussed, these are mainly the frequency bandwidth improvement techniques. Then I'll just focus on the technique that is gain improvement technique. In gain improvement also, we used to use the same and technique, sometimes the stacking technique. So what happens in this case, yeah, it is known as generally anisotropic stacking, because we are using the what happens, we can the similar, we can use here epsilon r1, epsilon r2, again epsilon r1 and r2, means the similar structure will be repeated, okay. These things we can repeat. So what happens in this case, how this is generally improves the gain. So when there is a continuous changes, when, because it is, we can see it is a microstrip line slot coupling, okay, and the energy, when the energy, like the electromagnetic, the energy just entered inside the DR, okay. So this wave started moving from here in, from epsilon r1 region to epsilon r2 region, okay. And we can see when it touches this boundary, then only there is a change of, there is a change of boundary, the boundary changes, okay. And once the boundary changes, what happens, the wave started moving to the other side where is the lower permittivity, okay, because we know air is the lower permittivity, because air has the lowest one, that is the 1, and epsilon r1, let's say it has 10 dB, sorry, epsilon r is 10, and here let's say it is 12, okay. So when the wave is moving from 10 to 12, generally it is, generally it gets reflected sometimes, and many things happens, okay. Sometimes it will reflect, sometimes it comes back again, started radiating again, it gets reflected. So in this moment, what happens, the wave started moving to the right hand side or the left hand side, or where the permittivity is lower, okay. So as this, when this procedure happens continuously, what happens, the wave started moving, radiating from the side wall than the top side. Of course, some waves will be radiating from the top side. I won't say that no waves will come out from the top side. It will come out, but the maximum radiation will come from the side wall, okay. And as the side wall, the radiation increases in the side wall, the increase of the radiation from the side wall compared to the top wall leads to improvement of both side gain or directivity, okay. So this is also one technique that can be used. We can use the stacking concept and the continuous repetition. If we started repeating the stacking like epsilon one different permittivity with the repetition, okay, so that will help in enhancing the gain also. The next technique that is very nice technique actually. This is the authors have used a horn plate. They have used a horn shaped, okay, horn shape around the DRA, that as we can see by looking into this antenna also, someone can easily say that the antenna gain is mainly directed topwards, okay, in this direction, and that is also reflected on the right side radiation pattern. We can see it has the lower backlobe radiation, not lower, it has some backlobe, but we can see the maximum radiation comes in the 0 degree, okay, we can see here. That is because of the placement of this horn, okay. Generally these two sides, these two walls obstruct the radiation, and they started redirecting the waves from this side waves, this side to front side, I mean top side. As a result, the gain also increases. So this is also a very basic uh, concept, because we know horn antenna generally radiates waves in a particular direction that helps to increase the gain. So this concept has been utilized for DRA. Apart from this also, the one of the techniques that is electromagnetic bandgap. This EBG technique is nothing but the passive loading effect that helps to enhance the gain of the antenna. EBG were realized in a to reduce and eliminate the surface waves. As we know that EBG technique is nothing mainly when we put it on the ground plane, the surface, it generally reduce the surface waves, and that leads to increase the directivity, bandwidth, and radiation efficiency. Okay, so this technique also very much helpful for increasing the gain or directivity. Okay, the next one that comes, it is also useful to reduce the side lobe and the radiation pattern. Of course, when we can see that the surface waves are reduced, of course it will help to reduce the side lobe, no doubt, and it gives the maximum radiation in the front, I mean board side. Sorry, it will give maximum radiation in the 0 degree. Okay, and hence the radiation pattern, that is front to back ratio and overall antenna efficiency is improved. So this technique is a good technique, but sometimes because of the fabrication problem, people generally rarely use this technique. But I'm not discouraging anyone, but this is sometimes we need to, before going when someone is implementing this technique, just think about the fabrication part, because if you are doing something and not able to fabricate, it doesn't mean anything. So this is also a good technique, can be used if the fabrication facility is available. And the next one that comes, superstrate loaded DRA. Superstrate loaded DRA is mainly works upon the principle of multiple reflection. Okay, and the multiple reflection is nothing but some people also tell it's a directly parasitic antenna that enhance the antenna gain. How this generally works, if we'll just look at this, okay. So there will be multiple, let's say this is the source and this is the incident wave that gets reflected from the superstrate, again reflects back. So in this manner, what happens, there will be multiple reflection, and once there will be multiple reflection, there will be highly directive waves that will come out from the superstrate. Okay, and those highly directive waves means, highly directive means of course the directivity will be better and the gain will be better. The effectiveness of the dielectric cover or the dielectric superstrate, it can be enhanced further by satisfying the resonance condition, which is a quarter wavelength air gap from the antenna. So that also depends on at what height we are putting our superstrate. Okay, we need to check all these things, but keep in mind this is nothing but the multiple reflection technique. But however, if you just look into the literature, generally the very basic papers that comes to only dielectric superstrate. On the left hand side, we can see the authors have used the standard technique. Okay, we can see how the gain has been improved by placing the superstrate, and this superstrate is nothing but this is the source. In this case, it is the source, and there will be multiple reflection. Once there is a multiple reflection, some waves, when those waves will be having the better energy, they started penetrating the superstrate and moves out from the superstrate. I mean that those are highly directive. And if we just look into the gain pattern, sorry, gain behavior, we can see the antenna 2 is nothing but the same antenna without superstrate, and the proposed antenna means this figure. If you just look into this figure, like there's a significant increase in the gain by using the superstrate. On the right hand side also similar behavior has been obtained, but here we will see this is exactly our work only. I think 2017 we have published this work, and here we can see DRA-3 is nothing but this final DRA that has been this figure, and by placement of this superstrate, I mean here we have not used a superstrate that covers the whole whole antenna system. We have just used the superstrate, narrow superstrate that is oriented in the direction of antenna polarization. Okay, And because of this placement, actually, we can see we have also compared without the superstrate and or without superstrate and superstrate. This DRA2 is nothing but this same antenna without the superstrate. DRA3 is the antenna which is shown above. If you just compare this blue figure and the red figure, of course, we can find this blue line and the red line. We can find that the gain has been improved significantly with some degradation in between. But however, the overall gain and the average gain is much better than the previous one. And there is also, as I told, that previous one is the only dielectric superstrate, and here people have used only metal superstrate. And this metal superstrate is nothing but just a thin, not properly thin, some millimeter, 1 millimeter, 2 millimeter thickness metal superstrate is placed upon there. And there also authors have also analyzed that not only the height of the superstrate but also the size of the superstrate. I mean, the length and width of the superstrate also matters. That controls the gain behavior. That is shown in the right hand side. We can see, okay, that is given in the right hand side. This is A and B. This is nothing but the length and width of the superstrate, this one. And we need to check it. We need to check at, for this one, for the size of the superstrate, length and width of the superstrate, still now, as I have seen the literature, no such mathematical formula is available. Just we need to check, with continuous variation of this length and width of the superstrate, we need to check at which frequency it is giving better performance. And as we see, this antenna is quite better, and it is giving a gain of around 12 dBi. So this is quite a significant improvement. So apart from this, also some people have also reported like frequency selective surface superstrate and metamaterial superstrate. This is nothing but that controls the resonant frequency and all these things. We can see here in the left hand side figure that they have used the multiple reflection technique. This is nothing but the multiple reflection technique, okay. And because of this FSA superstrate, they have achieved a higher gain. And this superstrate also nowadays also some people have used the superstrate. The pattern of the superstrate, how to design this FSS, all this pattern in which manner, so that the direction of the radiation, it can be changed. Okay, so that is sometimes nothing but the smart antenna kind they are talking about. On the right hand side, we will see the metamaterial superstrate they have used, and if you just compare these two figures, this graph. Metamaterial superstrate is quite helpful. It enhances the gain of around more than, it doubles the gain. By looking into this figure, we can say it just doubles the gain. Sir, I think it's time already.
Yes, please, you conclude.
Sir, those part I have. I think in the next session I can discuss.
Okay, fine, it's good. As such, there is no fundamental query from the participant side because you have presented the thing so nicely. I think each and everything is clear to them. Okay.
Okay, sir.
Yes.
So for the participants, just I would like to say that there are some other gain improvement techniques that in the next lecture we'll discuss.
Yeah, sure. With this, thank you very much, Dr. Sonik Kiran, once again.
Thank you very much, sir, for giving me to share my work.
Yeah. Okay, thank you. See you in next session. I think on last day, if I'm not wrong.
Yes, on the last day, 6:30.
Okay. Bye. Take care. Good night.
Thank you very much. Thank you, everyone. Good night, everyone.
Okay. Yes.
Should I close the meeting from my side?
Yeah. You close the. You can leave the session now. No problem.
Okay. Thank you very much.